ver si después en el break puedo encargarme yo con el OBS de la transmisión por YouTube.
Ya.
¿Ok? Gracias.
Ok, ahora sí ya estamos, creo. No sé qué hacer.
Está en live. A ver. Sí, creo que ya vamos a empezar. Es curioso verme por YouTube. A ver, entonces, un minuto más para coordinar algo. Ujú. Yo creo que ya estamos listos entonces. Okay, so switching language here. Sorry for the little difficulties, technical difficulties that we had. Things happen, so I really appreciate, and actually I'm really happy that we are here together for this REPU Seminar 2022. We are already ahead of time, but still, I still want to thank everyone to be here. I still want to thank the mentors that did a really incredible job this year for our first time online internship, not only for computer science, but for all their branches. So it was a very huge challenge, and I think the mentees and mentors and the head of the branches did an incredible work. Probably we will give some more details during the presentation, but we want to start right now. And what a better way to start by presenting our first guest speaker. So Leandro Medrano. Leandro Medrano, it's a physics from San Marcos University in Peru, doctor in Technischen Universität Dresden. Hopefully I said it right. In applied physics and engineering physics. So today, Leonardo, he's going to talk to us about integrating machine learning and multi-scale modeling applications to molecular systems. We are very happy to have you here, Leonardo. Sorry for the time, but we're excited about to hear your talk today.
Okay, thanks, Jorge. Thanks for the introduction. So, but just a correction, is Leonardo, not Leandro, but it's fine. So, I don't know if you can share my screen now. So, yes, maybe. Okay. So, can you see my screen? So,
yes.
Okay, I will point this here. So, yeah, I mean, as you say, so I did my master and bachelor studies in San Marcos University in Peru. And then I moved also to Germany for the PhD, and then now in Luxembourg, University of Luxembourg, doing my postdoc. So it's already 3 years there. And then in this presentation, I will talk about first a general view of this new field, integrating machine learning and multi-scale modeling. But so I will focus mostly on molecular systems. No? So well, this figure here, I will put a point. Where is the laser pointer here? So in this figure, so we try to summarize what it has been the last 10 years for this unification of machine learning and quantum mechanics. So as you may know, quantum mechanics is already has a long history, and all the methodologies that has been developing, but through time, but very slowly, no? So then now in the last 10 years, so machine learning came to save computational physics and chemistry. So in order to speed up all the calculations, and now we are trying to combine these two different research fields and try to see what we can do in that direction. So, and this is what I will base my presentation here. So we go to the next slide. First, I would like to start for introducing the work where I work in now. So here, so my group is the Theoretical Chemical Physics group, headed by Professor Alexander Tachenko. and it's located in Luxembourg. So I guess most of you, they don't know where is Luxembourg. Also, I didn't know before. It's so between three main countries like Germany, Belgium, and France. So, I mean, Luxembourg is very small compared to these countries, but it has been developing recently many research areas. So, for instance, the University of Luxembourg was founded in 2003. So it's a very young university, but the research fields, they are growing a lot, so like in the last 10 years. So this is the group where I'm working. So we have different master, PhD students, and also postdocs. And here's the head of the group. And these are the two buildings that we have, the two main campus. So so we have three different research areas in our group. One of them is machine learning and chemical physics. Then we also work a lot in no-covalent molecular interactions and in anon-biomolecular modeling. But in this presentation, I will focus mostly in the first case. So now, before starting to talk about the research that we are doing, so I will give a bit of background to explain you what was the idea before doing this integration between machine learning and quantum mechanics. So, as you may know, maybe some of you are familiar with the Schrödinger equation. So the idea here is to solve one fundamental equation in order to get all the information about the material and then try to compute the properties of the material or different kind of properties. But to solve this equation for a many body system or a system more than 4 or 5 atoms,
Leonardo, are you there? Leonardo? Looks like there was a problem. Leonardo, if you can hear me, you can say it in the chat because right now we cannot hear you. Let me try something. Oh, yeah. Looks like there was a problem during the presentation. So hopefully he'll connect again. Just give it a time. Okay. Let us check something before we continue.
Maybe we can start with our first mentee, and then we can move on when Leonardo reconnects, because it's only 10 minutes of their presentation.
Okay. Yeah, sounds good. Okay, so we will continue. Right now, we will start our mentees presentations. And let me see who's first one to go here. Okay, so Alessandra Latorre. She had her host university was Purdue University, and today Alessandra, she's going to talk to us about high resolution nano decimal spectrometry imaging for skeletal muscle fiber analysis. So this is our first talk of the meeting. Alessandra, let me know when you're ready.
Good morning.
sorry.
Can you hear me? Sorry.
Yes, we can hear you. Oh,
Okay, I will share my screen.
Give
And
us a
sorry for
moment.
the.
Yeah, Leonardo, we are going with the Alessandro's presentation, which is like 10 minutes, and hopefully we can restart yours. Is that okay?
Okay, it's up to you. I mean, I'm back already, so.
Okay, thank you very much.
Okay, can you see my screen, please?
Yes, we can.
Thank you. I just need a second. Okay. Good morning, everyone. It is a great pleasure for me to present you today the research I have made as part of the REPU chemistry cohort at Purdue University. The title of my presentation is Nanodesi Mass Spectrometry Imaging for Skeletal Muscle Fiber Type Classification, a project I have made with my mentor, Daisy White at the Julia Laskin Laboratory. So first of all, muscle composition has 4 types of fibers, varying from type 1, type 2A, type 2X, and type 2B. The type of muscle that we have analyzed is gastrocnemius skeletal muscle, placed in the back part of the leg, and it's in contact not only with the bones, but with the superficial tissue. And because of that, it possesses a differentiated metabolism that varies from oxidative and glycolytic. And also, it is related to the type of twitch that we generate with the activities, varying from slow to fast twitch. In the left part of the image, we observe an immunofluorescence image taken from the same tissue, where we can see the 4 types of fibers correlated with colors, and they possess a mosaic type distribution. These fibers are very difficult to analyze because the size is 10 micrometers and requires a high spatial resolution power. Also, because of the mosaic type distribution, we don't know if it's a preferable zone that is enriched for any specific fibers. So based on those difficulties and the challenge, we have made a study to characterize the metabolic profile of oxidative and glycolytic muscle fibers, and also to visualize biomarker localization with high spatial resolution chemical imaging techniques. But as I told you, it is a complex study to make. First of all, because normally mass spectrometry imagings don't offer high spatial resolution. And if we generate an image, it will be blurry in some parts. So we will not be able to recognize a mosaic type distribution based on mass spectrometry imaging. And also because the immunofluorescence image and the distribution type don't offer an information referring to what part is specific for a type of fiber, it is very challenging to correlate the immunofluorescence image to the mass spectrometry imaging. So that's why we will require a technique that optimizes the spatial resolution. Normally, mass spectrometry imaging techniques offer a resolution of 100 micrometers. And now we will work with techniques that optimize 10 times the spatial resolution. But before I show you what is the technique, let me define what's a lipid and how their composition can be different. I can show you now a phosphatidylcholine lipid that possesses a head group and 2 acyl chains. Each head group for a lipid will be different. In this case, phosphatidylcholine possesses a phosphate group and an amine group. And when we generate a mass spectrometry imaging, the fragmentation will be specific. So we will have a fragment of 125 Dalton for the phosphate group and 59 Dalton for the amine group. Also, the composition can be different. In this case, we have an 16 carbons and no double bond acyl chain, and also an 18 carbons and 1 double bond acyl chain. So the complexity of a lipid is unique and will generate a specific fragmentation pattern. So that's why we will be able to recognize every type of lipid by using this technique. As I told you before, there is a high spatial resolution power required. In nanodesi, mass spectrometry imaging, a technique developed at the same laboratory at Purdue University, will offer a great resolution power. The nanodistortion electrospray ionization process starts by impacting a solvent, in this case methanol and water, that will travel through a primary capillary and will generate nanodroplets that will cause a liquid branch where the lipids present in the gastrocnemius muscle tissue will travel and will be dissolved through a nanospray capillary, where the mass spectrometry inlet will collect this information to further provide fragmentation patterns that are specific for each type of lipids, and we can correlate the mass to charge ratio of these peaks with the X and Y axis to generate some mass spectrometry imaging. But as I told you before, normally the resolution power that mass spectrometry imaging works are very low. So in this case, we can see a phosphatidylcholine with 40 carbons and 6 double bonds with a resolution of 160 micrometers, where the image is very blurry. If we do nanodesorption electrospray mass spectrometry ionization, the distribution possesses now a mosaic type. So when we do nanodesi, we increase the resolution, the spatial resolution power, and we're able to correlate this with immunofluorescence image. Also, this technique doesn't require sample preparation, and it can work perfectly with 10 micrometer resolution, so it's very efficient. And now, if we compare both images, we can segment some specific parts of those images taken, and if we overlap them, there is a distribution that correlates with each type of fiber. So that's why we were able to generate information of the 4 types of fibers and to see their enrichment. With this data, we were able to work and generate also information about the metabolism and the acyl chain composition. So among all samples, we had approximately 120 lipids. And of those lipids, approximately 45 were oxidative and approximately 28 were glycolytic. So we were able to differ not only the type of fiber, but correlate them with the metabolism. And there were some lipids and metabolism that don't show a pattern. And now if we analyze from the different metabolism, the composition of the acyl chain, that is this part of the lipid, we were able to recognize for oxidative fibers the high presence of 18 carbons and no double bond acyl chain. That is very unique because if we analyze glycolytic fibers, it is a high presence of 16 carbons and no double bonds acyl chain. So now we have unique information that corresponds for each type of metabolism. Now I would like to show you how mass spectrometry imaging generated with high resolution power by nanodesi mass spectrometry can represent the mosaic type distribution. And we can see now that there is a transition between no presence correlated with this bar, with no presence of lipids and high presence of lipid. And the transition is very gradual. Now in the left part, we have oxidative fibers, and in the right part, we have glycolytic fibers. And for glycolytic fibers, the transition will go from a high enriched zone to a zone that possesses no presence of this type of lipid, right? So because the transition is not narrow, it provides a great result and shows that the transition between oxidative to glycolytic metabolism in fibers, it's very easy and can be done by varying not only the energy expenditure, maybe with the exercise that we do every day. So based on those results, we can say that firstly, the metabolic transition is facilitated. Secondly, that there is an oxidative enrichment in species that predominates among glycolytic enrichment. And thirdly, the acyl chain 18-0 was predominant in oxidative fibers, and 16-1 is predominant in glycolytic fibers. So with those results, we can now set some future directions. For example, high-resolution nanodesi mass spectrometry imaging have shown to successfully characterize and visualize individual skeletal muscle fibers, so can be applied to similar studies. Also, in this case, we analyze gastrocnemius muscle from a tissue that doesn't possess a specific disease, but we can correlate this information and apply to study the method across diseases. And last but not least, we can do dietary fiber research for a better understanding of the health benefits of dietary fibers as well as muscle training. And well, lastly, I would like to say thank you to the Julia Laskin Laboratory at Purdue University, and also to my mentor, Daisy in CY, and the REPU program for everything. So if you have some questions, I will be pleased to answer them.
Thank you very much, Alessandra. That was incredible. So actually, I have one question related to, I don't know how much you explore this, but I'm curious about the relationship of the length of the acyl chains and how that can make a decision if which pathway use, if the oxidative or glycolytic. Have you explored a little bit about that?
Well, I can show you the information that we obtain related to acyl change composition. In this case, for example, oxidative fibers possess a length of 18 carbons, 22 carbons, 20 carbons. Normally, the highest length that we observe is 24. It is not really predominant, a presence higher than that, basically because of the stability and the abundance of lipids in the tissue. And the short one that we observe is 14 carbons and 16 carbons. But the metabolism is not related with the length of the acyl change. It is correlated with the type of fiber that is in this tissue. So for example, if in this lipid, we observe a high presence of type 2A fibers with a length of 20 carbons, it will be specific.
I see. Okay, thank you very much. Very good job. Now I think we can, you can stop sharing your screen and we can continue. Actually, to go back to our first presentation, I'm very sorry for the difficulties, Leonardo.
I was my computer. No, don't worry. Sometimes the computer, they are not so trustful.
Okay, please continue. Where were you?
Can you see my screen now?
Yes, we can.
Okay, great. So, okay, so I mean, we just summarize it, try to do it faster because we are with the time now. So, so the sharing question was postulated in this year, 1926, but since at that time we were not able to study more than systems like a 2-atom system, 2-body systems, then we need to develop new approaches to study more realistic systems like proper materials or molecules like more than 10 atoms. And that's why one of the most well-known approximations to solve this Schrödinger equation is the density functional theory, which was postulated at the time of 1964. But it took around like 34 years to win, for instance, the Nobel Prize, which is a very good, the most recognized prize in chemistry. Also. But so this is the level of the approximation like was developed at that time. But also, this approximation has some problems, no? Like, for instance, depends on the type of material we want to study, and also is kind of limited to the size of the material. For instance, we cannot study materials with more than 200 atoms, let's say, so there is a limit there, because it's very computationally expensive. So that's why in the 2000 years, so like then new methods appeared, like semi-empirical methods, which use more approaches than density functional theory to solve the Schrödinger equation. And now we can study systems at the size of DNA chains and so on. But all these simulations, they also takes like a considerable number of time if we want to go for realistic systems. No? That's why here is where machine learning comes in action, because the idea is to use machine learning techniques in order to speed up all the calculations by keeping the same accuracy. Just to summarize what I mean by accuracy, so here we have this pyramid, so with the different levels of approximations to solve the Schrödinger equations. For instance, we can go from empirical potentials of force fields to some empirical methods, approximate density functional theory methods, and then we can go to full correlation methods or quantum Monte Carlo methods, which are more precise than the other ones. But if we want to get precision in the solution of this equation, so we will also need to invest more time for the computational calculation. So, and this is a problem, no? Because for instance, in some countries, we don't have very good supercomputers to perform these kind of calculations. Then we need to figure out how to deal with these simulations without requiring this kind of supercomputers. So that's why we want to try to integrate machine learning with quantum chemistry. No? But the idea of machine learning is not new. So it comes initially from the 1952, where they didn't know, but they already start working with machine learning techniques to, for instance, play this game, checkers. So, and they already start developing some algorithms to tell the computer to in which path to move the every tail there now. So, and then, but since the computers were not so good at that time, so they stay only like solving so simple games, or developing methods like k-means, like a way where they didn't need like too much computational resources. That's why there is a gap between the first algorithms developed, machine learning algorithms developed at this time, and the first applications that we saw for chemical physics. So there is a gap of around 32 years. So this gap, it comes together with the evolution of all the computers, not like IBM computers and so on. So now we have the computational power to use the algorithms developed at this time and to apply to real physical or chemical systems. So that's why in the last years, so this group, DeepMind group from Google, so they developed this AlphaGo and AlphaFold methods. For instance, AlphaGo was developed to play games, but so they, for instance, they managed to defeat the champion on Go. So like, that was a good achievement for this field. But now recently, so like 2 years ago, so they developed this AlphaFold method, and they could predict predict the structure of proteins or very large biomolecular systems, as you can see here. And this in the fraction of second, like we were doing before with this molecular dynamic simulation, semi-empirical methods. No? So we have gained a lot of time here, like doing the same calculations and also keeping the accuracy in the calculations. No? But so if you want to know how this is done, so I will just try to explain very general view. So first we need a database. So we need data to apply some machine learning techniques. For instance, in these games, so that they were like developing all these steps of the procedures, how the game is done. And they were introducing this information to the computer, and the computer was learning. So in this case, but nowadays what we do is that generate a database of, for instance, properties of the material, composition of the material, and so on. And then we introduce it to a machine learning black box. Sometimes people, they don't know exactly what is inside the black box, they just use it. So after introducing the data here, so we get our machine learning model. And then, so if we have the model already, so then we can predict any kind of property of the material or the compound. And then we could think about applications in certain devices. For instance, here's an example. So you have an input image. So if you don't have enough data for something, there are some techniques like you can distort your data. You can reproduce data with a reduced data that you have. And then you have a reasonable data size of database. And this is introduced to a training process. And then you have to train the model and also test the model and so on. And you start optimizing the parameters inside the model. And then after optimization, so you get your model, and then you can think now of applications like some devices or other things that you want to do. So if we go now to this idea connecting to some chemical physics problems, we have this, for instance, in material science. So in material science, you know, like there are many elements, and also you can generate from these elements many compounds like 2D materials or van der Waals structures you can see here. Then you can make experiments. You can do some computational calculations of these materials, and then you can get different kind of properties. So all these properties, they will generate your database for these materials. So then you will have all the information to describe this material, and this will introduce a certain machine learning model you will develop. So these models can be supervised or unsupervised learning, which I will not go in details, but you can use two different approaches there. And then at the end, so you will be able to do material predictions. So that means like based on the properties that you want in this material, you will be able to say, okay, the material
Okay, it looks like we have some technical difficulties again. We'll just give some minutes to Leonardo. We're fine. Don't worry, guys. We're just going to give Leonardo some minutes so he can come back. Actually, very interesting when he was talking about AlphaFold. It's kind of revolutionary in the biochemistry area right now. So just stay there and we will connect with Leonardo soon. Just as a reminder to all the mentees, so as you know, we had some problems at the beginning, so we are going to just keep going with the same order of presentations. Alessandra Latorre already made her presentation, so the next mentee will be Jairon Narro, but we're going to give some minutes to Leonardo so he can come back and continue his talk. I'm just going to follow with the order of the next mentees presentations would be Jairo Narro, then Marco Peña, then Steve Waman, and Alejandra Inostroza, and the last one of the first group will be Arturo Flores. We should give, so we're just going to give just a couple of minutes. And we'll try to fit the same schedule for the second part of the seminar. So we'll see if we can still start the second part at 1 p.m. Okay, let's finger crossed and let's hope for that we can start the second part of the session at 1 p.m. So let's wait a little bit and see if Leonardo can come back with us. Great. Yes, so he's coming back. Leonardo,
sorry,
this is, it's fine. This is kind of a special day today for all of us.
I don't know why this computer is failing today, but so.
But yeah,
I will try to finish the presentation on time. So
it's fine. You should do it. You were in the physics part.
Yes. So I mean, so as I was saying, so here, so we want, so you can generate a database from the experimental computational point of view using any kind of properties, so describing the material as you wish, so, or depending on the application that you want to do at the end. So the idea is to train the model to predict the property that you want or you are interested with. And then also you can make the prediction of, depending on the properties of which compound you can get. No? So you can predict materials based on the properties you want. And then you can do screening of the materials if you are thinking in the terms of applications as well. So to generate, for instance, the electronic devices, optoelectronic devices, and so on. So. Also, what you can predict is like, for instance, STA image of the two-dimensional materials or molecules over surface, and also like X-ray diffraction patterns, as you can see here. And also you can analyze how the conformation of certain materials, clusters, molecules, they change over certain temperatures. So you can make, nowadays you can make prediction of different kinds of materials, and these methodologies are used also for the design of materials, not only for properties, also for the design of new compounds. And this is reducing the amount of time like you were before using in the lab, for instance, you take like 1 or 2 years to get a new material maybe, but now with this idea of using machine learning, so it could take you maybe a month, or you can reduce also the number of experiments you have to do in the lab to produce new materials and then think on applications. So this is the idea in general. So then, one of the main approaches that we use in machine learning is called neural networks. Why? Because it's related to neurons. So then neurons, you have the dendrites, and also you have the nucleus, the cell body, the axons, and the axon terminus. So we try to connect neurons in different way, and then you have, for instance, here the axon for another neuron connecting to these dendrites through these signals. No? And then all the information is so here we do the operation of the input with this weight, like we call it. So then this is coming as information in the cell body. Then using this activation function, so in the cell body, then we get an output. So it will be the output axon, which will be connected again to another neuron. So this is kind of the procedure that they follow internally in this black box I showed you before. But since one neuron is not enough, as you may think about, so in our brain, so then we have to connect many neurons there. So that's why we have, so from the methodology part, so we have our input layer with different kind of information, which is connected to a hidden layer, which contains like a different, let's say,
Okay, again, we're having some technical difficulties. Neural networks. Well, I haven't been very deep in the area of neuroscience, but it's I find it incredible how neural networks can connect so much right now, and try to translate all the experiments that we have seen in C. elegans, mice, flies. It's a very interesting part, actually. So I think it's fair to just give Leonardo the chance to let us know what he wants to do. So just as a reminder, since we had some problems earlier with the transmission, the mentees are still supposed to give their talks in the same order. Still stay with the time frame that we set for your 10 minutes presentation. Hopefully that will help us to be on time for the second part of the meeting. We will give some announcements at the end of the seminar, just for the mentees. Okay. Related to when they are going to have like an extra meeting with us. Today is just about their projects, about their research of their internship, and we will have an extra meeting with them just as a final gathering for the cohort of 2022. Okay, so it looks like Leonardo will have some problems to connect again. So we just have to keep moving and continue with the next Menti presentation. So next we have Jairo Narro. Jairo Narro had his host university like as Purdue University, and today he's going to talk to us about automation of bitmap files, generation for the fabrication of micron nanostructures with a focused ion beam. Okay, Jairo, you have the floor.
Yeah, good morning, everyone. Oh, sorry. Okay, okay, sorry, I have a little bit of problems with my camera, but can you see me now?
Yeah, try to share your screen, please, so if we can see your presentation.
I'm sharing my screen. I hope you can see it.
Yes, we can see it.
Okay, great. So I'm going to start. Good morning, everyone. I'm going to present a research project that I developed under the guidance of Dr. Rosa Diaz from Purdue University. It's the automation of bitmap file generation for the fabrication of micro nanostructures with a focused ion beam. So first of all, let's talk about what does a focused ion beam do. And a focused ion beam is an instrument that focuses a beam of ions in the specific point of a sample in order to remove materials from its surface. And in combination with an scanning electron microscope, this is a powerful tool to fabricate and prototype devices at the micro nanoscale. And the process looks something like this. When the ion beam hits the sample, the atoms that are at the surface of the sample are removed, and these removed atoms are called spotter material. So focused ion beam allows the fabrication of micro nanostructures with high precision. For example, focused ion beam allows the generation of micro and nano patterns of different geometries, and in this case, we have nano holes that have applications in, for example, plasmodic devices or biosensor devices. Also, we have you can generate more complex geometries like this georoot that can be part of the mechanisms of a micro electromechanical device. Also, you can generate micro or nano channels that will be part of radio devices, and it has applications, for example, in the analysis of biological samples, molecular separation of biochemical assays. And finally, you can do something even more artistic like this nano Chinese pan. So the question is, how do we control the geometries that we want to fabricate with the focused ion beam? One way to do this is by generating a bitmap file with a desired structure and then imported this bitmap to the FIB system. And there are some important parameters that must be taken into account in order to obtain an accurate structure. And the first one is the dwell time. And this is the time that the ion beam remains in one specific spot. Also, the passes are the number of times that the beam scans an area, and the beam current is the number of incident ions, and this defines the diameter of the beam. So if the pixel is white, then the system uses the maximum dwell time, but if the pixel is black, then the pixel is skipped. Pixels with values in the range of 1 to 255 are linearly interpolated. So what we want to do, first, we want to automate the pattern creation process for bitmap files. And second, we are going to use these generated bitmaps to fabricate some structures and evaluate the performance. So we're going to first define the number of pixels. For example, let's say that we have a milling area of 10 by 10 micrometers. And if I set the bin diameter to be 400 nanometers and the pitch value to be half the value of the bin diameter, then the overlap will be 50%. And I will need only 50 pixels in order to reach the desired dimension of the structure. So we can define the number of pixels by the relation between the dimensions of the binding area and the pitch value in the x and y direction. The pitch value is something important because it defines the overlap. And if you have the recommended value of overlap is 50% or a little bit more sometimes. So this ensures to obtain a smooth surface in the sample. So the resolution is also affected by the bin diameter. Let's say that we have a milling area of 5 by 5 micrometers and an overlap of 50%. If I set the bin diameter to be 26 nanometers, then I will need more than 300 pixels in order to generate a bitmap of, for example, the REPU map. But if I have a really large value of bin diameter, for example, 300 nanometers, I will use less pixels to generate a bitmap, and we will see that we are obtaining some deviations from the ideal structure. So defining an appropriate bin diameter value is essential for the process. So I developed an interface in Python to automate the patterning creation process, and as you can see here, the user can define the bin diameter value, the overlap value, and calculate the pitch value next to the milling area. So you can change the number of pixels and generate the desired patterning for the structure. Also, the interface allows the generation of arrays of different geometries for micro nano patterning process, and the user can define the size of the array and the separation between these different geometries. So these are some of the patterns generated with the interface. We did some experiments with the bitmap of the REPU map, and we can see here that this accumulation at the atoms of at the borders of the structure are called redeposition, and this is a really common effect during the process. Here, these are the atoms that are removed, and instead of moving away from the surface, they start to deposit here at the borders. Also, we see here that we are not obtaining a smooth surface, and this material that we use to fabricate the structure is a 3-phase semiconductor material, and that has a low melting point. Next, we use a silicon structure. We see here that we avoid the reposition effect at the borders, and also we obtain a really smooth surface. So this looks pretty well. And in a moment, I will do a comparison why this happens. So also the interface also allows the generation of 3D patterns. And in the case of 3D patterns, the difference with the bitmaps that we saw previously is that in this case, this is not only black and white. We are generating a grayscale. So this means that the depth at each point is going to be different. So the dwell time will vary according to the profile function of the structure, and the user can define this profile function by 2 simple inputs for the 2 most common 3D structures. This is quadratic structure, and this is a big group structure. So by defining this, the interface will generate a suitable grayscale to fabricate this structure with the FIB. So we fabricated a 3D structure first in the 3-phase semiconductor, and we see here that even when it's following a profile, the desired profile that we want, the quadratic profile, we are now obtaining a smooth surface. And also, we can see here some redeposition effect of the borders. But in the case of silicon, we are avoiding the redeposition effect, and we are obtaining a smooth surface and actually a really good structure. So this happens because silicon is a really common material used for fabrication of prototyping, and we know what is the volume produced value for this material. Volume produced is simply how much volume of the material are removing by the number of ions that are being that are here in the sample. But in the case of 3-phase semiconductor material, we don't know the value. and we are using, we are considering the values for other material, and this is not something not good. So if we want to fabricate something in a material which we need to know that the volume for those value, and this is different for different materials. So in conclusion, we developed an interface that enables fast and automatic generation of patterns for the fabrication of microstructures with a focused ion beam. And this will be really useful for the people that are in the laboratory, because it facilitates and makes the process more simple, and also speed up the process of generating a bitmap files and then importing it to the FIB. And also, this is really helpful, especially for the people that has different backgrounds and are not really familiar with the utilization with the use of a focus ion beam to fabricate an structure, because the FIB has applications in different areas. Finally, the structures fabricated in silicon have a smooth surface and no red position of the workers, instead of the other 3-5 semiconductor material, which if we want to fabricate something in this, this material has to be, we have to study what is the volume for those value of this material. And finally, this set the basis for a future work that is correct the bitmap file values to reduce deviations in 3D structures by using a FIB milling simulator and computational algorithms in order to obtain even more accurate structures. So special thanks to Dr. Rosa Diaz from the Nanotechnology Center at Purdue University. And thank you everyone for your attention. And if you have any questions, I will be more than happy to answer.
Thank you very much, Jairo. So can you elaborate a little more about that FIB future directions? Like, how do you think it's going to improve
yeah,
3D structures?
For example, here we're obtaining in this 3D structure the desired profile that we want, but unfortunately, due to and as you can see here, the redeposition effect is at the borders, but the redeposition effect is also here, but instead of the borders, some atoms might be placed here at the bottom of the structure. So this is not so simple to see. You can you should measure the distance here and compare it with your ideal structure, and you will find some deviations at different points. So the basis for the future work is to correct the bitmap file values, taking into account these position effects and other deviations, in order to obtain more accurate structure with the ideal profile and reduce this difference, this little difference in the values of the profiles, because we are talking about the nano and micro scale, so this small difference can be actually really significant. And there are some simulators that will help you to simulate the process, taking into account these different effects. And if you apply some computational algorithms, you can calculate different values for the pixels in the range of 1 to 255, and maybe obtain a more accurate structure.
Nice. Thank you. It's been amazing seeing your work during the months. So congrats. So thank you for your talk, Jairo. Right now, we're going to try something. We want to see if we can go to YouTube streaming. So Omar is helping us with that, and will be just let us know when we should continue. So the idea is that this presentation of the mentees can be shared to a general public. That's been always the way these seminars have been worked, but we had some problems at the beginning to do the Facebook Live. So now we are trying to go for the YouTube streaming. So Omar, let us know when should continue with the next mentee, so we can start not only listening to the presentation, but also...
Sí, dame un ratito. 1 second.
Okay, so now we were streaming live by YouTube, but right now we have all the accommodations that we needed at the beginning. Okay, so now this should go even better. Okay, so up next we have Marco Peña. Marco Peña had a host university, Harvard University, and today Marco is going to talk to us about dynamic control of neurotransmitter release at antennal lobe of the fruit fly larva. Marco, we are very excited to hear you talk today, so whenever you're ready.
Okay, can you see my screen?
Yes.
Yes.
Yeah, nice. Hello, everyone. I'm going to present the results of my project. The title is Dynamic Control of the Neurotransmitter Release at Antennal Lobe of the Fruit fly larva. My mentor is Luis Hernandez Nunez, and the PI was the Professor Arvington Samuel. Well, as introduction, the simplicity of larva early olfactory system make it a workable model for olfactory research. The larva of Drosophila melanogaster just have 21 olfactory receptor neurons, so and each other responsive to one other receptor. In contrast, the adult has 120 olfactory receptor neurons type, so many neurons. And the mice has millions, 10 millions of olfactory receptor neurons, so way many neurons to study. So this is the advantage of the larva. The larva has few olfactory receptor neurons. However, despite the simplicity of this olfactory system, it shares some feature with the mammalian, and I'm going to explain one. One receptor type per olfactory neuron and one glomerulus for all olfactory receptor neurons of one type. And you can see it in this figure. For example, these red neurons that is connected with the red receptor, so sensitive to one specific odor. And all these red neurons go to one glomerulus. Here in the glomerulus, all these neurons are connected with projection neurons, and the projection neurons send information to higher processing centers. This feature is the same, literally, in mammalian. We have these red neurons, for example, going to one glomerulus, and these glomerulus, they are connected with microcell, and microcell are projection neurons that send information to the cortex, which is a higher processing center. An interesting fact is that the discovery of this organization of the early olfactory system in mammalians gave the Nobel Prize in 2004 to Richard Axel and Linda Bach. So for this reason, the fly is a good model to model the olfactory system of mammalians. In specific, I study this part of the system, the antennal lobe, and more specifically, I study the effect, the interaction between inhibitory neurons with these axon terminals of olfactory receptor neurons. And I'm going to explain a bit more about this. These inhibitory neurons or local neurons, the same. Local neurons control the axon terminal neurotransmission. For example, you can see here, a rotten fruit. And rotten fruit is like the food for fight. So the odor of this fruit activate the soma, and thus generate a spike of electricity that runs through the axon of this neuron. This is the olfactory receptor neurons, and ends in the axon terminal. In the axon terminal release neurotransmitter to the projection neuron that send information to higher processing centers. This axon terminal release neurotransmitter activating this. But this arrow, the black arrow, is the excitation arrow. But also activate the soma of the local neuron, the inhibitor one. And this local neuron give negative feedback to the axon terminal, so controlling all this releasing of neurotransmitters. This arrow is the red arrow, the inhibitory neurotransmitter. And this is the place, and this is the place, the glomerulus, and antenna lobe. So my research objective was explore the dynamic control of these local neurons over the neurotransmitter release of excitatory alpha-3 receptor neurons. And to do so, first I started obtaining data, experimental data from calcium imaging data. The calcium is an indicator of neuronal activity, but doesn't correlate perfectly with the electricity of the neurons, the real activity. So I'd used deep learning package from Python, Cascade, and some stochastic process to model the events, the spikes of currents at the axon of alpha-3 receptor neurons. So from the calcium data, I infer the activity of the neuron, the electrical activity. And then I use this electrical activity as an input for dynamical simulation of the neural interaction between the local neuron and the alpha-3 receptor axon, alpha-3 receptor neuron axon at antenna lobe. Well, the first experiment was testing if there is a differential modulation of the true activity between two classical inhibitory neurotransmitters. So local neurons are releasing also neurotransmitter, inhibitory ones. So the GABA, for example, is one neurotransmitter, and inhibitory neurotransmitters is one example. So I have this neuron model that I model with differential equation. I also model the axon terminal with another system of differential equation. And the GABA local neuron also a question. So I'm simulating the system with math. Yeah. As a result of this simulation, I'll calculate the release of neurotransmitter of the axon. Yeah, I also model the input to model the activated or inactivated state. So there's some activity even when it is when the alpha-3 receptor neurons is inactivated. It is so like the passive properties of the system. And I also modeled another neurotransmitter, the glutamate, with the same thing, the same feature, the same equations. 5 seconds of simulation, 10 replicate per experiment. And this is important, the release of neurotransmitters to the local neuron, because it's correlated with the release of the neurotransmitter to the brain neuron that are sending the information to higher processing centers. And so my result one is GABA reduces the vesicular release of excitatory neurotransmitters at the alpha-3 receptor neuron axon terminal better than glutamate. And you can see it in this picture. So this is the number of released vesicles, and we have this situation, the GABA control over inactivated alpha-3 receptor neurons, the glutamate case for inactivated, and the activated cases also with GABA and glutamate. And you can see the GABA is controlling better the release of neurotransmitter here and here. So they are more efficient in this way. Well, I will give you a bit more background for my next experiment. So the network of local neurons indirectly connects alpha-3 receptor neurons. So the activation of one local neuron for an alpha-3 receptor neurons can indirectly inhibit other alpha-3 receptor neurons that are connected to this neuron. So in this way, so the activation inhibits alpha-3 receptor neuron 2 and 3. But there are also a red network of local neurons. So these local neurons inhibit this local neuron, so generating dynamic perturbation to another alpha-3 receptor neuron that is connected to this local neuron. So this is interesting. So I set up an experiment, a theoretical experiment also. Experiment 2, which is intended to explore the effect of one activated alpha-3 receptor neuron over the other alpha-3 receptor neuron. So here I model literally all the alpha-3 receptor neurons, 21 alpha-3 receptor neurons, and all the local neurons, the 15 local neurons, the green one, the glutamate, the GABA also, GABA local neurons. I use the real connectivity from the connectome of the larva, and I use also this system of differential equation of the axon, of the soma, of the synapse, and 8 seconds of simulation. Yeah. Also, yeah, this is the input. I activate specifically one olfactory receptor neurons to see the effect over all the other olfactory receptor neurons. So the activation of olfactory receptor neuron has a non-homogeneous effect over the release neurotransmitters of other olfactory receptor neurons. And you can see it in this plot. This axis is the activated olfactory receptor neuron. So I am activating this. And this another axis, the x-axis is the effect over the other olfactory receptor neurons. And the color is the change in the vesicle release, red to white for enhancing, purple to black for inhibition. And you can see it. There is some enhancing, there's some inhibition, and it's a bit complex, this plot, but I will explain with one example. This olfactory receptor neuron 49A that is sensitive to the odor of one predator, the parasitic wasp. So in this case, this olfactory receptor neuron is inhibited by this food odor, but is also enhanced by others, but these are olfactory receptor neurons. So there's some, like the odor of the food is like inhibiting the presence of danger, maybe for reach some food, to explore for more for food. And there are also other odors that are correlated evolutionarily to the presence of danger. So there is this fine tuning of these neurons. In other words, we have these olfactory receptor neurons that I confirm that there is some inhibition, but I also have evidence of increased excitation. In conclusion, different inhibitory neurotransmitters lead to differential modulation of vesicle release of phytosteroid neurotransmitters. So the glutamate against the GABA again, and the activation of one olfactory receptor neuron can lead to enhancing or reduction of vesicle release of excitatory neurotransmitters of other olfactory receptor neurons, my experiment 2. And the future actually explore the combinatorial activation of multiple olfactory receptor neurons, for example, this and this. So if there are some synergisms or antagonism between different olfactory inputs. And special acknowledgement to Professor Arvington, to my mentor, Mr. Hernandez, for Julio, Brenda, REPU mentors, and the rest of other REPU mentors and REPU organization. Thanks for your attention.
Thank you, Marco. Good presentation. We have a question here from Mac Aguirre. He's asking, I have curiosity of your model. Is there any way to corroborate that your model is correct? How do you know the results you get are not false results?
Yeah, well, there is ways to analyze the, I'm gonna, with calcium imaging, we can just like test, like do a specific experiment to this action terminal and calculate the activity of this action terminal. This is a way, but we cannot do this for all the possibilities, all the neurons, because there is some technical difficulties there. But we can confirm this effect, for example, these olfactory receptor neurons and how this specific, so like the modeling is like eliminating some possibilities and focusing and like reducing the possibility to some specific neurons, so we can do an experiment on this specific neuron and this another specific neuron, and in this way we don't have to do experiment for everything in the system. This is the advantage of doing simulations.
Okay, Marco, I have something to a question about when you show the results about the release of neurotransmitters between GABA and glutamate. You said that GABA kind of reduces the release, but don't you feel also that the basal release of mediated by glutamate it's already high? Like, have you checked actually that the difference between the increment of inactivated with activated?
Yeah, there are differences between inactivated and activated, but there is a difference. But between inside a group of inactivated, there are different between GABA and glutamate. So yeah, there are different between those states, inactivated and activated. But inside the state, we have the GABA is different with but glutamate with the GABA, and the GABA is like controlling better than the glutamate in both these cases.
Okay. Okay, thank you very much. It was a nice presentation, Marco.
Thank you.
So we have next Steve Waman. Steve Waman had Baylor University as the host university of the internship. And today Steve is going to talk to us about generative adversarial graph convolutions network for Peruvian Sign Language data augmentation. Okay, Steve, whenever you're ready.
Hi, everyone. Please let me know if you can hear me while I'm using my phone as a hotspot.
Yeah, Marco, please can you stop sharing your camera and then we can continue with Steve. Yeah, we can see your slides.
And can you hear me?
Yes, we can hear you as well.
Okay. So, good morning, everyone. My name is Steve. My mentor is Gisela Bejarano. I'm today going to present the work that we were doing in Baylor University. We call this Generative Adversarial Graph Convolution Network for Peruvian Sign Language Data Augmentation. So to begin with, what is the Peruvian Sign Language? As other kind of sign languages, the Peruvian Sign one has three main features. That is the hand shape, the location on the body, and the motion. So here we can see three different signs. Ministerio, bonito, no aprende. Why is it important to face the sign language processing? Well, sign language processing stands for the processing, the automation, and the generation of different sign languages. But the problem with this sign language in general is that exists many barriers for the sign language user, because most of the technologies that we use today are focused on written forms or spoken forms. So the technologies such as personal assistant, Siri, and Alexa are focusing on the people. And also in sign language, we have a great diversity in sign language execution. This is based on ethnicity, geographic region, age, gender, and education. With sign language processing, we can generate, for example, automatic transcription. In this case, for example, this person is performing a sign, so we can transcribe the sign that she's doing. For example, hello. Well, in particular, in Peruvian sign language dataset, exists a problem. The problem, to begin with, this dataset was proposed by Bejarano, among others. And this particular dataset has problems because more than 400 signs that we can see here have less than 10 instances, and only a few ones have more than 15 instances. And that's bad because a huge amount of data is required to perform or to train a good algorithm to, for example, recognize signs. And that's why there are methods to cope with that problem. For example, one of these methods to cope with that problem is the data augmentation. In this case, we have two methods, the classical methods that are focusing just on changing the pixel level features. That means that they add noise to some images. But in fact, the video is the same. The information is just changing at the pixel level feature. On the other hand, we have methods based on generative adversarial networks. In this case, they are based on machine learning algorithms in which we can train. We can generate different samples based on training a neural network with data. So taking into that account, our objectives, the first one is to take advantage of the graph representation from the sign language based on key point lemmas. So we can see here joints of the skeleton that we can capture because it's an inherent structure of the body. Another objective is to increase the number of instances of Peruvian signs from the use of generative adversarial networks based on graph. And finally, we want to measure the contribution of this augmented data. We rely on this architecture that was proposed by Bruno de Gardin to generate sign actions. Actions that, for example, jumping, cooking, and so on. But we are using this architecture to generate signs because both of them share things. For example, the handshake movement these particular movements. And this architecture is based on two modules. The first one is the generator that tries to generate fake samples in order to confuse the discriminator. So the discriminator is going to decide if the sample that is fed into that is real or fake. And this generative adversarial network is based on graph. That means that in each block we are using the information of the graph, in this case, the information of the body of the skeleton. This architecture also has this conditional generative adversarial network. That means that we are putting the class label or the sign label in order to say, okay, I want to generate this particular sign. With that, we can generate an intermediate latent space that feds into this generator. With some noise injection, we can generate, or we can add stochastic variation in the generated samples. And finally, well, another change that they use is that instead of using the common binary cross entropy that is used in GANs, they use the Bas-Einstein GAN with gradient penalty that has promising results. So how we can get our data set? Our data set is composed by videos of different signs, and we use a 2D pose estimation model to get the key points of a video. For example, in this case, we are the video is Ministerio, for example, and the output is this one that has all the landmarks that we are going to use. Because in this case, we are just using the modality of the landmarks. That means that we are not using the RGB frames or the information frames that we could also use, but in this case, we are just using the landmark modality. So with that, we can construct a graph. In particular, this model retrieved 33-point landmarks. So we want to have a data like this form, where n is the number of signs, c is the number of coordinates, x and y, t is the number of frames, and v is the number of landmarks or vertices or joints. And that's how we construct this previous sign language graph. In this case, we use just 23 key point landmarks in order to focus on the information of the hand. And that's why we get just 23. So in this case, we are also using 10 number of frames because we are subsampling all the videos to 10. If a video has less than 10 instances, 10 frames, sorry, we add some frames at the end, repeating some of them. Which is the metric that we are using to measure the results? We are using this phase inception distance that tries to measure the distance between two distributions, the real and the generated ones. For example, in this case, we can see that this image is generated, and with the image has at the high disturbance level, the FID is higher. And with the image is Y generated, we have the FID almost 0. And those are our results. For example, in this case, on the left, we can see our generated samples. On the right, we can see our real samples. Sign, comer, bien, and pensar. There are 5 different samples. We can see that there exists a variation between each of them. And the information, also the hand shape and hand movement is almost equal to compared with the real ones. And we measure the phase inception distance that I mentioned before using the different data sets. For example, in this case, we experimented with 15 and 10 frames, and we also variate the number of instances per sign. We found that when we use a higher number of frames, the information or the FID is higher. That means that at the end, the number of frames is losing information, so we can generate the signs correctly. But with this configuration, we got a good results. And my conclusions are that despite the number of different generated signs that is a lower number of signs, just 3, the FID score suggests that the real and generated signs are close to each other. We also thought or experimented with the use of a spatial temporal graph convolution that is used in the state of the art, exploits the skeleton structure better than CNNs or RNNs. The greater the number of frames, the lower the FID that I showed before. And as a further work and in future work, we are going to focus on the hand movement, just having the landmarks of the hand to focus on that information, because that's how people perform the sign language. So that's all. Thank you very much. If you have questions, I'm glad to answer.
Thank you, Manuel, Steve. So actually, I have a question. You mentioned that this was mostly focused in hand movement, but I noticed that in those structural graphs, they can even tell assign values to the face, like mouth, eyes. How do you think that will change? I would understand mouth, but the eye region is what makes me curious. Like, do you know if that provides also relevant information when do this kind of analysis?
Thank you for the question, Jorge. That's a good question because, as I mentioned in conclusions, this is the work that we are doing right now. We found that these points or these landmarks that are based on the face are not providing information that, good information, because the movement or how people perform that science, they use the hands. So it's not relevant to use the mouth or the eyes, just maybe 2 points to have this graph structure. But that's an experiment that we are doing on that.
Okay, we have another question from Leonardo. He asks, could you explain how do you generate the noise in the data, and how do you know how much noise do you need? Active learning?
Okay, thanks for the question. You mean that noise, right?
Yes.
Okay. This is a random noise just for stochastic variation, as in this case. How much noise do you is your length? It depends on the feature length that you are that you want to use, the feature embedding, which I would say, or the feature vector that you are putting into this mapping network. So, for example, if I decide to use a vector of 124 or 1024, I could generate a random noise. This is Gaussian noise of length of 1,000, for example, and then I can put the Y information to concatenate it with that noise, and then putting into this generative model. But it depends on the experimented. It is usually to have 1,024 or 512. That's the common length that they use. But yes.
Okay.
Yeah, but can I ask another thing?
Yes, sure.
Yeah, but also depends like how much you distort the image, for instance, no? And then, you need to control this, no? Like otherwise, you distort the data completely, and then the learning won't be good. So.
In this case, we are not using images. I don't know. Maybe you can explain it better, please, to understand.
Yeah, I got from the next plot. I think you try to reproduce the representation is kind of this one, like yes. You introduce this is the question, like how do you introduce all this information, like I only want to rate and then with some certain numbers. So this was not clear for me. So
you mean how I use the graph?
Yes.
Okay. Yes. In this case, the conditional is just to add a stochastic variation, but the graph and the adjacency matrix that we got when we use a graph is used in each block. So, for example, in this case, I'm using the special adjacency matrix because when we got the graph, we can see how they are connected. So, with that adjacency matrix and the graph, we are using the information of the graph.
Actually, why you need to use the basset gun? So, I know like some people use it, but so what you gain compared to the other ones?
Yes, the basset gun is demonstrated to have better results because when you use a binary cross entropy, you have these flat regions, and when you do the back propagation procedure, you can exploit the gradient. So it's better to have the base histogram because it is not bounded. It's unbounded. The loss that it provides you is not between 0 and 1. It's just a minus. It can be a real number. So that's the gain of the improvement in this case.
Okay, thank you.
Thanks for the question, Laura.
Okay, thank you very much, Manuel. That was very interesting. And I think we can continue with our next presenter. So up next, we have Alejandra Inostroza. She was working with her mentor hosting at University of Luxembourg. And today, Alejandra is talking about machine learning predictions of physiochemical properties of molecular systems. So super interesting. So Alejandra, whenever you're ready.
Okay, thank you. I will start sharing my screen. Okay, good morning, everyone. I'm Alejandra Nostroza, and today I will introduce you to machine learning prediction of physicochemical properties of molecular systems. We predict or calculate the properties of molecules or materials using computational chemistry methods. These methods present a trade-off between accuracy and computational cost, since performing more accurate predictions implies a higher computational cost. There are efficient methods for studying very large systems, but they lack precision, while other pretty accurate and reliable methods requires a lot of computational resources. Thus, in the middle of these two opposing sides, machine learning appears as an alternative to balance accuracy and computational cost. By combining computational chemistry methods with machine learning approaches, we may be able to perform fast and accurate predictions of molecular properties and the results of chemical reactions. In this internship, we will focus on the former. There are two types of physicochemical properties: extensive properties that depend on the size of the molecules, and intensive properties that depend on the composition or electronic structure of the molecules. And there are many efforts in trying to predict both types of properties. The prediction of extensive properties has successfully improved over the years, while the prediction of intensive property has presented some difficulties and is a current field of research. In this internship, we wanted to apply the knowledge of previous investigations so that we can predict relevant, extensive, and intensive properties for small and large and complex molecules. In order to achieve this, we first need to represent a molecule so that the computer can understand our input data. And to do that, we use descriptors. Particularly, we use two descriptors. The column matrix descriptors, which represent a molecule with a matrix whose coefficients depend on the nuclear charge of the atoms and column potential energy. And also we work with the bag of bonds descriptor, which represents each type of bond in a molecule with a vector whose elements are computed as column potential energy. And we use these two descriptors to represent a set of small molecules to predict an extensive property, and a set of large molecules to predict an intensive property. We also need to specify our regression model. In this case, we use the kernel-rich regression model, which computes a property following this equation. These alpha values are called regression coefficients and can be computed following this formula. And this K object is called kernel and can be chosen between these two options, Gaussian or Laplacian. So our data set will be split into two subsets. The first one will be used for training the model, that is to compute these regression coefficients, and the remaining molecules will be used to test and validate the model. That is that we use this equation to compute a property for these molecules, and then we compare our results with the reference data of the out of training set. Furthermore, here we can identify two parameters that we can optimize. sigma and lambda. So we can vary sigma and lambda so that we can minimize this mean absolute error for the prediction of an extensive and an intensive property. For example, here we reach a minimum of the mean absolute error when sigma is equal to 5,000, and here we reach a minimum when lambda is equal to 10 to the minus 2. And we have repeated this analysis for all the descriptors and kernels that I have presented you before. Well, we use these descriptors and this model to predict the atomization energy of a set of small molecules and the lipophilicity of a set of large molecules. The atomization energy is an extensive property and is the energy needed to break up a molecule into its constituting atoms. For the prediction of this property, we use the QM7 database, which contains 7,000 small molecules with between 4 to 23 atoms, and looks like this one, whose values of atomization energy go from 500 to 2200 kcal per mole. On the other hand, lipophilicity is an intensive property and is related to the ability of a molecule to dissolve in lipids or oils. And for the prediction of this property, we use the LiPo database, which contains 4,000 large molecules with between 12 to 98 atoms, and looks like this one, whose dimensionless values of lipophilicity goes from minus 1.5 to 4.5. And from now, the left side of the slides will be used for the prediction of atomization energy, and the right side of the slide will be used for the prediction of lipophilicity. The first plot I would like to show you are the learning curves of the prediction of atomization energy and lipophilicity. Learning curves are plots of the mean absolute error of the prediction in dependence of the number of training samples. And here we can notice that as we increase the number of training samples, we reduce the mean absolute error for the prediction of both properties and independent of the type of descriptor or kernel that we are using. Then we can also check the correlation plots. That is a scatter plot of the reference data versus the prediction values for different kernel functions. There is the Gaussian or the Laplacian kernel. And for these plots, we can compare the dispersion along this equilibrium point. And what we are looking for is for a small dispersion, because that means that we have prediction values that are more similar to the true values of the reference data. And then we have a more accurate predictions of these properties. So considering that, we can state that the back of the Laplacian kernel give us more accurate results than the Gaussian kernel, because it presents a smaller dispersion than this one. Last but not least, we can also compare the distribution of errors for the prediction of atomization energy and lipophilicity, but for different molecular descriptors. That is the column matrices representation or the bag of bonds representation. And for these distributions, we can compare the standard deviation of the distributions, because when we have a small standard deviation, that means that we have errors that are close to zero, and then we have more accurate predictions. And considering that, we found that the bag of bond descriptors give us more accurate results than the column matrices descriptor, because it presents a small standard deviation for the prediction of atomization energy and for the prediction of lipophilicity. In conclusion, the bag of bond descriptors and the Laplacian kernel give us the most accurate prediction of atomization energy and lipophilicity for the data sets that we have used. This is also a good example on how quantum machine learning can enable us to predict extensive and intensive properties of small and large molecules. But it's a fact that the prediction of intensive property requires more sophisticated descriptors than the one that I have used, because we have to include, or we may need to include the electronic structure of the molecules so that we can improve the prediction of these intensive properties. Also, I would like to point out that quantum machine learning allows us to perform multidisciplinary research because we cannot only focus on the physics or chemistry of the research, but we can also extend the study to biological systems, as we did for the study of lipophilicity, because it has applications on drug discovery. And finally, I would like to remark that there's a lot of work to do in the research field because we can not only improve the prediction of intensive property, but also we can improve the prediction of physical chemical properties for larger and more complex molecules with hundreds of atoms. And that's all. Thank you for your attention, and special thanks to my mentor, Leonardo Medrano, who has been the kindest person with me the whole time that I have been in the internship. Thank you. If anyone has any question, feel free to ask.
Thank you very much, Alejandra. Very impressive work. My question maybe would be very more general, like about your experience. Like, what would you say that was the most challenging part in this process?
I think the optimization of parameters, it was sometimes, I was sometimes worried about the time that my code has been running because it takes minutes or hours. So every time I was repeating and repeating and repeating, so I can find the most, the best parameters for the model. I think that was the hardest part of the internship, but above all, it was actually a really nice experience to me.
Nice. So we have a question. We have two questions. So first from Alessandra Latorre, she's asking, do you think it could be applied to study solubility, and what modifications would require? Would it be intensive or extensive?
Okay, in the case of solubility, I don't know what type of property is, but we can actually extend the studies of quantum machine learning to all properties one can imagine. But we have to consider that we need descriptors or representation for the molecules that fit the type of property that we want to predict. Because as I have mentioned, maybe geometric descriptors as column matrices or bag of bones are good for extensive properties, because as we increase the size of the molecules, we can obtain larger values for that property, and we can fit the descriptor to the prediction of that property. But for intensive property, we need to consider other qualities of the molecules, like their composition, the electronic structure, maybe long-range interaction, and that kind of things. So there's actually some work in trying to improve that descriptor so that we can predict, accurately predict some specific properties.
Okay, thank you. And also Leonardo is asking, are your machine learning models transferable and scalable? What do we need to predict the same properties for unknown molecules?
For unknown molecules, I don't, for materials, I have read a paper about it, like not working only on molecules, I think like larger molecular structures. So depending on the model or the types of descriptors that you are working, we can talk about scalability or transferability, because we can maybe with a certain type of descriptor or model, we can study systems that are larger than the molecules that I have presented you, and also molecules that are more complex, talking about the types of elements that they contain. So depending of, I think that in this case is the basics, but there are many studies that tries to make the descriptors and models transferable to a larger amount of properties and molecules.
Okay, thank you very much, Alejandra. That was amazing. Very good job.
Thank you.
Okay, so up next, we have the last Menti presentation for this, for the first part of the seminar. So we have Arturo Flores. Arturo Flores had as host University of Rhode Island. And today he's talking about similarity of MLP mixers representations. So Arturo, whenever you're ready, you can start your presentation. I cannot hear you if you are saying something. Oh yes, you are muted. Okay.
So please, can you let me know if I'm talking and you can hear me?
Yes, we can hear you and we can see your presentation.
Great. So hello everyone. Today I will talk about my REPU Computer Science project in this seminar. I titled my project Similarity of MLP Mixer Representations. I've been working this with Professor Marco Alvarez at the University of Rhode Island. I hope that you'll enjoy this presentation. As an introduction, I would like to bring to the table state-of-the-art algorithms in which image recognition and classification is a very well-known problem. To the left, you have Mark's ArcCNN applications for object instance segmentation, in which you can see that people's silhouettes are being segmented like in these figures. And to the right, you have the attention of learner position by a visual transformer, in which the model is telling us which part of the image is the most important. With CNNs and BATs, we have the standard models for computer vision applications nowadays. In that regard, MLP Mixer, simply Mixer, is a technically simple but powerful solution. Mixer was first introduced in 2021 and is a model mostly based in multi-layer perceptrons. Why Mixer should be interesting for the AI community nowadays? For three main reasons. First, it's simple. Second, it is computational and affordable since it doesn't rely on convolutions or self-attention layers. And third, it is competitive, 76% of accuracy, just 3% below a BAT. Moreover, the problem of understanding the neural network representations remain relatively underexplored. So that's why more validation should be conducted to render Mixer an strong option. So the main idea behind my project is to study in deep Mixer's performance and to provide more insights to the scientific community. So with that, let me introduce Mixer architecture, which is conceptually simple. Here we have the global architecture of Mixer. We have here the inputs for Mixer, that they are turned into patches. These patches go through a network and the end reach a fully connected layer that is going to predict the class. We're particularly interested in these Mixer layers. Inside them, we have two multi-layer perceptrons. The main difference between them is that their inputs are transformed using a transpose operation like you can see here. Inside each MLP, we have two fully connected layers and a GALE activation function. So with that, you can see that Mixer is really simple because it relies on MLP, and I will use this model for my whole experimentation. Another concept that I would like to bring to the table is the concept of a representation. Imagine that we have two layers, layer A and layer B, and then each of them has 5 neurons. We're going to pass a data set of 9 examples. After passing the data set, we're going to take the output of each neuron to each example, and then we can form this matrix. This resulting matrix is going to be a representation, in this case, representation X and representation Y, as you can see here. We can say that a representation is the neuron's response to an stimulus. In my project, I'm going to take representations from Mixer, and then we will find ways to establish a comparison. Indeed, we will use center kernel alignment, CKA, because it's a consistent similarity measure. So we are doing this to the representations, we're multiplying this way. Then we are doing the inner product. Then we normalize the expression with the Frobenius norm, and then we're going to take this resulting expression that has a centering matrix, H, and then is using a linear or RVF kernel, as you can see here. So with that, we're going to call this expression a similarity measure. And this similarity measure is going to provide us with a quantitative result, a number, that is going to allow us to know to which extent a representation X resemble a representation Y. So that is the main idea between comparison and taking inputs from Mixer. We studied Mixer from a similarity perspective. We use similarity measures to conduct experiments. In this case, we vary architecture parameters in a fine-tuned fashion. Let's say we fix the number of layers and then we vary the embedding dimension. That is the width of each mixer layer. And then we do it vice versa. Second, we explore internal behaviors of MLP, of both MLPs, MLP1 and MLP2. Why we are following this order? Because we want to do this approach. We want to understand what is happening with the model, and then we go deeper and try to provide insights to the community. The first result is that we easily compare two representations with CKA. So you can see here two representations. In this case, representation for the layer 1 and representation for layer 6. For a layer mixer, in this case, we pass through the network this figure. We can see that visually these representations are very similar. However, if we are strict and we do a CKA RBF, the result is going to be 0.16 out of 1. Another result is that CKA unveils desirable patterns in mixer. So if we repeat this process of comparing two representations, but not with just two, we do all the combinations between a mixer model, in this case, mixer with 8, 12, 24, and 32 layers, we're going to obtain these heat maps. In this case, something interesting is that we have huge blocks for these two models of high similarity. That is not desirable. Why is not desirable? Because we are expecting that each layer is learning different representations, and that contributes to the learning itself of the model and then to the accuracy. As a matter of fact, we have that for these models that have huge blocks of high similarity, we're going to obtain a performance really low, as you can see here, compared to these ones. So it's nice to see how we are corroborating what we can visually see in a heat map compared to the final result after training of our mixer models. With more corroboration, we isolate each of these layers, and then at the head, we train a logistic regression, and then we train these independent logistic regressions for each of these cases, and then we plot these curves. In this case, it's also nice to see in the first layer that the curves is going up for models that are performing well. And then for these models, almost in the middle of the curve, the accuracy plateaus. So that is not desirable since we want to have this increased pattern. Moreover, more similarity among layers mean sometimes less accuracy. In this case, we did it not just with the depth of the network, we did it with the width. In this case, changing the embedding dimension. And it's interesting to corroborate that we have here huge block of high similarity in which, yeah, it has the lowest accuracy compared to the others. One interesting remark to this is that even though we have here a huge block, for the others, we do have also medium blocks of high similarity. And so that's why we can speculate, we can hypothesize that we have really 75% that is not that good. I mean, for state-of-the-art models, we will expect more accuracy. However, even that mixer is competitive. If we study specific patterns before and after training, we're going to identify some interesting behavior. In this case, if we take an A-layer mixer, we're going to identify that here's a pattern that then is intensified, as you can see here. And it's interesting to see in which side or in which parts of the model we're going to obtain a high accuracy before and after training. If we go deeper in the model and we take the representations from MLP1 and MLP2, we're going to take this pattern before training a grid pattern, and then this grid pattern is going to turn into something like this, in which we see that the very first MLP1, not MLP2, is going to have similar representation, and it goes darker as we go through the network, as you can see here. So with that, some takeaways that I would like you to understand is that our study provides more insights about MLP mixer. First, more MLP mixers do not represent an increase in their performance. Internal MLP1 of mixer layers learn similar representation. Third, CK shows an appropriate correspondence between similarity and accuracy performance, as you saw in the heat maps. Next step will be that in a future project or a next internship to optimize mixer by using pruning techniques. Finally, this was a great research-based summer break. I would like to thank MS candidate Alex Lachans for helping me in all the experimentations. Thanks to Professor Marco for his mentoring and guidance through the internship. And third, thanks to all my colleagues, REPU, and all mentors in the CS branch for giving me encouraging feedback to improve my project and presentations. In general, this internship made me love more AI. Thank you for your attention. I will be more than happy to answer any follow-up question that you might have from my presentation.
Thank you, Arturo. That was great. I would like to know a little more like the pruning concept that you're mentioning as your future steps. Can you elaborate what that means or what that involves?
Yeah. So this is a suggestion for a future project. Since we have a limited amount, it will have been nice to include it in our project. However, a pruning technique will mean that if we are having high similarity, highest really huge blocks of high similarity, it will be nice to do some pruning. I mean, to drop out, let's say, or to take away some neurons or some layers that are not contributed to the learning set and to the learning itself, and reduce these huge blocks. So the main idea behind that is that when we talk about pruning. Thank you for your question.
Okay. No, thank you to you. I think all the mentees here in the first session have shown like it's been a great summer for you guys, and really we're very proud of you. So I think this is the end for the first part of the seminar. So sorry at the beginning for the difficulties, technical difficulties sometimes happen, but I think we will be more than ready to continue at the second part. Now we have a break. So according to our schedule, we should be coming back at 1 p.m. With another guest speaker, Daisy Unsiwan. She will start the second part of this seminar. But right now we have a break. So for everyone who is listening through YouTube.
Jorge, sorry for interrupting. I was just wondering if Leonardo, do you think you can? Would you like to finish your presentation? I don't know.
I already
if
talked
you
to
are
him.
able to solve your issues.
Yes, I already talked to him. I think since the difficulties that he had at the beginning, I'm not sure that can be solved. So he mentioned that he'd rather just to continue with the normal schedule of the program.
Okay, great.
Okay, so thanks everyone who's been listening to us, who's been watching us, and the mentees. We can continue this. Okay, so I think we see you later then. We will continue this at 1 p.m.
you're ready, just give me a heads up. Hi, everyone. It's very nice seeing you again. I would like to welcome you to the second portion of the REPU seminar. We'll be hearing very nice talks of our mentees, and we also have an invited speaker that is going to kick off today's sessions in the afternoon. The invited speaker is Daisy Siwai. She's an alumni from National University of Engineering, and currently she is a PhD candidate at the chemistry department at Purdue University. And she's going to tell us about her work titled Uncovering Lipid Isomers in Biological Samples with Mass Spectrometry Imaging. Thank you, Daisy, for your time.
Well, thank you for the invitation. So let me share my screen. Can you see my presentation?
Yes.
Yes. Is it on presentation mode for you?
Yes, that's correct.
Okay. Yeah, well, thank you so much for the opportunity to present my work. My name is Daisy Siwai, as Kevin mentioned, and I'm going to talk about my graduate research journey at Purdue University. I'm currently a PhD candidate. I'm in my last year of grad studies at the Julia Laskin Lab at Purdue University, and my field of expertise is analytical chemistry, especially in mass spectrometry. And I'm very excited to talk to you about my research. So just as an introduction and a motivation for you, like when we hear about mass spectrometry, maybe there is nothing familiar to you, but I want to show you some examples of how mass spectrometry can be applied in the clinical research, which was my first motivation when I heard about this technique. So imagine that we have a tumor, and then you are going into the operating room, and the clinician, the surgeon, needs to remove that tumor. Generally, this procedure is done by eye. So the clinician just removes the tumor as part from your body, but he doesn't know any other means to evaluate if he actually has removed all the tumor that it's in your body. So the way how mass spectrometry it's been applied recently is that once we can take a biopsy from the tissue, and the tissue then is sectioned and analyzed with these instruments, these mass spectrometers. And when we can create, and by training some algorithms, we can train the instrument to tell us where the healthy region and the unhealthy region is located. So this can become a more automated process, and therefore, like, it can predict whether the cancer tissue where it's located, and it can do it in less than 10 seconds. So with this information, and if it's applied at the time of the operation of the surgery, the surgeon now can remove better this tumor from the patient, and therefore the patient doesn't have this need to go back again to another second surgery to have this tumor removed. Another means to apply mass spectrometry, it's also to find out what's the type of bacteria or virus that is causing disease. So for instance, generally when you have some sort of infection, you will start presenting some symptoms like fever, and based on the symptoms, the physician might believe this is an infection, but if it's an infection, they will prescribe you some antibiotics, but not all the antibiotics work on the same work efficiently for the same type of pathogen. So they need to figure out what's the pathogen that's causing that infection. So they can take a sample from the patient and analyze it with mass spectrometry, and then they can find out based on the profiles of this of the virus of the pathogen, we can find out what is the pathogen that is causing the infection, and therefore target that treatment with a specific antibiotic. So that really helps to accelerate the treatment, and rather than waiting for a couple of weeks until this infection it takes all over other places in your body. So this is the main technologies that are being developed in the clinical research. In my lab, in the lab where I work, we don't do these clinical cases, but we develop methods and technologies that can eventually be translated to be applied in the clinical research. And we are definitely trying to tackle down different challenges that are associated with it, like the ion suppression, because when we are sending all these molecules to the instrument, there is a lot of competition for signal, for charge. So what happens is that there are some molecules that ionize better than others and therefore are not detected at the same time. And sometimes those molecules that are not well detected are the ones that are the most important. So I'm trying also to tackle down those issues. Also, most of the techniques that are developed are more qualitative than quantitative. And when we talk about in the clinical research, we really care about quantifying those biomarkers that are especially to detect certain diseases. And also, we really also are trying to push the boundaries of high resolution. So we always want to get a resolution better than single cell. So if we can improve that at no expense of the throughput, then that's also something that it will be very important to translate those technologies into the clinical research. So that was most of the challenges that I wanted to tackle down in my research. And the way how I did it, it's using a technique that was developed by my PI, Julia Laskin, at the Pacific Northwestern National Lab. She brought that technique to Purdue University at the same year that I joined Purdue. This technique is called the nanospray desorption electrospray ionization, which stands for nanodesi. And this technique is I think it has the potential to be translated into the clinical research because it has many advantages. First of all, this nanodesi, it's comprised of two capillaries, as we can see here in this picture. We have a primary capillary and we have a spray capillary, which are forming a liquid bridge. So this liquid bridge, once it lands on the tissue, it allows the extraction of all the species that are there. So we can extract metabolites, lipids, proteins, depending of the type of solvent that we use, we can extract all of those species at the same time. So those molecules will travel through that spray capillary and will further ionize at the inlet of the instrument, in this case, the mass spectrometer, and then we can detect them in the instrument. So the beauty of this technique is because it's ambient, so it can work under native conditions. So we can use it in the operating room. So we don't need to modify the sample. It's as it is available in the nature, we can analyze it. We don't have to modify it. Because it's a solvent extraction technique, we can modify the solvent as we want. We can add some reagents to enable reactions. We can modify the solvent to enable the extraction of certain type of molecules. So it's very flexible. It allows you to play with the solvent as you want, as I mentioned. And also, we can reach very, very high spatial resolution. In this case, better than 10 micrometers. Which is, it's a lot in comparison to other imaging techniques that are available right now. So here on the right side, we can see a palette or mosaic of some images that are generated after extracting all of these molecules from this liquid bridge. So every image that we see represents a molecule that was extracted, and all of them are obtained at the same experiment at the same time. So here just to clarify, because we will use this type of color bars in the next slide. So like 0 means low abundance of this molecule, and yellow to white means very, very abundant. So these are an example of high resolution images that we can generate from the nanodesi technique. And we can see these samples are from a uterine sample, which the size of that is very small. It's 1 millimeter, but we can, with this high spatial resolution, we can differentiate those very small features in the tissue. So my research focused on using that technique, but also the type of molecules that I analyzed was mainly lipids. I mean, we think lipids, sometimes we think about like that they are not good molecules for our bodies. We think about fats and triglycerides. But lipids in general, they have a lot of roles that in nature, like they can be part of your membrane, they can act as signaling molecules, they can act as building blocks of the members, as I mentioned. So those are very important molecules. And my research mainly focused on trying to characterize and find different abundances of those lipids across different samples. So this is a structure of a phospholipid, which is a molecule, it's just a representative molecule of the structure of any lipid. Here we have the head group, here we have the glycerol backbone, and here we have 2 acyl chains. And generally, with traditional techniques, what we can identify is just the head group and the acyl chain composition, which will tell us what type of lipid it is, whether it's a triglyceride, whether it's a phosphatidylcholine or a lysophosphatidylcholine, or maybe it can be just a fatty acid. So that kind of information is what generally we obtain with the conventional mass spectrometry approaches. But if we want to know like more deeper information, like where the double bond location is, or whether this is an SN1 or SN2 position, or whether this double bond it's on cis or trans geometry, so those techniques they fall short. They cannot give you that information. And what happens is that information is very important because now it has been implicated in the development of some diseases. So when I learned about this, I wanted to develop methods that can actually accomplish this other task. So first of all, I focus on just identifying where the double bond location is. And I try to develop approaches that can help us to identify those either by carrying out a reaction or adding some sort of separation to our methodology that can help us to distinguish those molecules from the pool of all the molecules that we have. And as I mentioned those molecules are actually important because it's been recently discovered that they can be implicated in the development of some diseases. And here is an example of that. Here we have a metastatic lung, and this area that it's indicated by the tumor, that's indicated by the arrow indicates the tumor area. And if we just map the distribution of this lipid that contains one double bond, then we can see that this molecule, it's depleted in the tumor region. But in this paper, the authors develop a method that can actually differentiate where the double bond location is. And they found out that this molecule, it was not just one molecule, it was actually 2 molecules that contain a double bond in the carbon 9 position and a double bond in the 11 bond position. So here, what it's telling us is that when we map the distribution, the relative distribution of this isomer delta 11 over delta 9, we can see that delta 11 is enhanced in the tumor region, which is very different to what we would observe with traditional methods. So that actually tells us that if we're able to map those distributions, now we can maybe observe these molecules as a biomarker. So that's very important if we want to translate that into the clinical research. So therefore, I was trying to develop technologies that can help us to figure out that. And it wouldn't be the first time that someone is trying to develop these double bond position identification methods. Actually, there have been a lot of research in the last decade trying to accomplish the same task. On one side, we have derivatization methods, and the way how they work is that they modify the chemical structure of those double bonds by carrying out a reaction that is happening on the fly, but generally it takes like 30 minutes to be stable. So, and on the other side, we have ion activation methods that they require you to modify the instrument, to add some lasers, to add some modifications to the instrument, which maybe it's not that accessible for any research lab. So I wanted to lie in between those techniques, those approaches, and develop a method that can actually enable a fast conversion of those lipids, the double bond of those lipids, that it won't require any instrument modification, so it can be adapted by any research lab. And it can also be accessible in the way that it's inexpensive. So anybody can do it in your own lab. So I wanted to lie in between those amazing approaches and try to develop something more original. So here, this is the approach that I developed. This is the nanodesi technique that I showed you previously. And the only thing that I did is just adding rose bengal, which is a photosensitizer. I was trying to look for reactions that can happen very quick. And then when we think about reactions that just can act on the fly, the first thing that comes to my mind are photochemical reactions. So because you just activate them with light. So therefore, I added a photosensitizer to the solvent. And then, but it will act similar as any other nanodesi experiment. So we have the solvent traveling through the capillary, then we have our liquid bridge. It will land on the tissue, extract the lipids, and then once it's near the inlet, that is the room for the opportunity for us. So then we can apply a laser pointer, the one that you use for presentations, and then by just irradiating the solution, we can generate singlet oxygen in the solution, which can react with the double bond and derivatize the molecule. So here it's a closer view of the nanodesi probe. So we can see here the capillaries are very tiny. We actually have to use some special cameras to be able to align them and position them in front of the instrument. And here is the area that I irradiate with the laser pointer. And this is a view of the actual experiment. So here, this is the cerebellum part of the brain. Here we have your primary, your secondary capillary. And if you look closer here, we can see there is a droplet that is actually running through the tissue. And that droplet is the thing that is extracting all the lipids from the tissue. And once they reach this area, it's where they are being converted into hydroperoxides. Okay, so the way when we think about singlet oxygen is the excited state of ground oxygen. So, and what makes it very reactive is that if we look at the electrical orbital diagram here, we can see that they have an empty orbital. So that makes it very reactive towards electron-rich molecules. And when we think about electron-rich molecules, those are the polyunsaturated lipids. And here, this is the workflow of the reaction. So here we have our lipid with the double bond. Then once we irradiate it with the laser pointer, we generate singlet oxygen, and that generates hydroperoxides at either side of the double bond. And then we send those molecules to the instrument, to the mass spectrometer, and we apply some fragmentation. We bombard the instrument with nitrogen molecules that will collide with the lipid molecule, and then therefore we will produce fragmentation. So it will give me pieces like a puzzle that then I can figure out where the double bond location was in the unreacted lipid. So it will clip in this part and in this part, and then I can figure out where was the double bond location previously. So that's pretty much the summary of all this idea. So if we look at the spectrum, here we have our molecule. It's a lyso-P. Right now, the names are not important, but just want to point out that for every double bond that you have in your molecule, it will produce a hydroperoxide product. So here, if we have just one double bond, you will create one hydroperoxide. And here, when we have a phosphatidylcholine 36-2 with two double bonds, you will generate two hydroperoxides. And therefore, when you have a triglyceride with three double bonds, then you have three hydroperoxides. But always the first product of the reaction is the most abundant, and it's the one that I generally use for my experiments. So the idea of this project is to be able to identify where the double bond location is. So this is just a proof of concept experiment. I made a mixture of two isomers. They have the same molecular formula. It's just a double bond position. It's different. Okay. So here, this is just a fragmentation spectrum of these isomers, and they just a first glance, we cannot see a lot of difference actually, because they are phosphatidylcholines. They will have specific fragmentation patterns. So they will clip here, losing a head group that right now is not important, but the number is 59, and another head group number that is 183. So both of them have the same fragmentation pattern. So if we look at this, we don't find any differences. But once we do the reaction and cleave where the hydroperoxide group is located, then we can find peaks that are unique for every isomer. So if we click here for carbon 9 and carbon 10, we will find a peak of 669 and 710, which are not found on the other isomer. And because they contain those head groups, they will also undergo the neutral losses that we observed previously. But also those are unique for this isomer. And when we look to the other isomer and we cleave here on carbon 6 and carbon 7, where it's the hydroperoxide is produced, there we can see that those are also unique peaks that we won't obtain them in the other spectrum. So because they also have the same head group losses, they will undergo the same fragmentation. But again, they are unique. So this example explains us that with this reaction, we can generate patterns that will help us to identify specific bond locations in the molecule. So therefore, we wanted to translate that into an imaging experiment where we can actually see how those isomers are located in the space, in the tissue. So there here, this is an average mass spectrum of a line scan collected with a nanodesi probe in tissue. So here, this is a molecule, 814, it's a hydroperoxide product. And when I look at the peaks, there I can find peaks that are unique for every isomer. One that has the double bond position on delta 11, and the other one that has a double bond position on delta 9. So here what we observe is that here we have the image of the cerebellum area of the brain. We have the white matter, the gray matter, the granular layer. And when we just image this molecule without fragmenting, no fragmentation at all, it's just the intact molecule, there we can see that this molecule is enhanced in the gray matter and it's depleted in the white matter, okay? But when I plot just the peaks, 712 and 684, then and place them as a relative ratio of the other, then I can see like very striking differences. So for instance, here I can see that the delta 9, it's actually enhanced in the white matter, and the delta 11 is depleted in the gray matter. And we won't be able to obtain this result without doing this fragmentation and this derivatization. So if we were just to use a traditional methodology, then we can just observe this type of image, which will differ differently from this one. So definitely that was very exciting for us, and we wanted to optimize this method in such a way that eventually, maybe from now in a couple of years, we can it can be like a routine tool to identify lipid isomers. So what we find out is that if we change the solvent and use some deuterated solvents, we can enhance or extend the lifetime of singlet oxygen. And that will help us to have better yield of the reaction. And the way how it would translate is that we will have better yields, and therefore we can detect more species. So for instance, here we have a molecule that it's called lysophosphatidyl ethylenamide, which has that one double bond. And just with our traditional experiment, we find out that we could identify two isomers, delta 9 and delta 11. So this is the sagittal region of the brain. And we find out is that we could detect the delta 9 isomer, but the delta 11 is very blurry. So we could barely see it, just mainly in the white matter of the cerebellum, but that's all. But when we changed the solvent and made it deuterated, we can see that we enhance the signal almost by a factor of 20. And we can see now that we can detect delta 9 and delta 11 distribution, which will be a little bit different. So here is a summary of all the species that I can detect now with this deuterated solvent, which is very exciting. Now we can analyze all these species, like 30 species at the same time, which is a lot for this type of methods. Generally, other methods just do 1 or 2 species at a time, but this is very powerful. Now we can do 30 at a time. And that was something that we are still trying to keep optimizing it. And I hope I can get some results in the next months. So the other point to tackle then was to whether this method can be can be used for quantification. So I wanted to explore that by preparing different solutions of delta 11 and delta 9 isomers, which are the ones that we always find in biological samples. So I prepared different mixtures containing different ratios. So here, for instance, if we talk about sample number 3, the composition of delta 11, it's 4 times delta 9. So I spotted on liver tissue, and I just liver mainly because liver, it's pretty homogeneous. So it will account for any matrix effect that we have in the tissue. And here, these are the number of the solutions that we have here in this table. So when we do the imaging part, we can see that there actually are, we can detect those different signals in accordance to their molecular composition. So for instance, for the mixture number 3, we saw that delta 11 was 4 times higher than 9. We can see the same here in this figure. So then we just made simply a calibration curve where we can see that when we plot the relative intensities towards the relative molar composition, then we can see that it's pretty linear. So it tells us that we can use a calibration curve to quantify the actual abundance of those isomers. But also we have almost a slope of 1, which tells us that, that the delta 9 and the delta 11 isomer, they can equally ionize. There is no a preference for an isomer to react than the other one. So that's also pretty good news. So, and we can apply this correction factor when we try to find the accurate abundance of those isomers. So the next part was I wanted to develop a method where we can actually quantify those relative abundance in every area of the brain. So here, this is our optical image. This is again the sagittal section of the brain. And this is just a representative ion image that I used to do segmentation. And here we can do the we can see the segmentation image where we can observe the different parts of the brain. And we generated mask where we can just select that part of the brain that we are interested and quantify all the molecules that are in that area. So these are the masks that were generated through this image. And the way how we apply this was basically, we have our delta 9 and delta 11 isomer, and we can see that indeed they have different abundances, different spatial distributions, where we can see, for instance, delta 9, it's enhanced in the white matter, and delta 11, it's depleted in the white matter, and it's also more abundant in the white matter than in any other part of the tissue. So we can calculate or plot the intensities of delta 11 over the total intensity of all those isomers. And we can see that indeed, like, it's pretty similar to what we observe here, but now we can overlay the different masks that we generated in the previous slide, just to select the pixels that are enriched in every area. And with that, we can replace that in our calibration method. And we can, again, calculate the exact abundance of that isomer. So for instance, if we want to know what is the relative abundance of the gray matter, we can see that it's around 0.42 composition of delta 11 and 0.58 composition of the delta 9. And similar, we can see that the white matter and the corpus callosum are the ones that are less abundant in delta 11 in all the different parts of the brain. So that is pretty exciting for us, because now we can tell exactly what are those relative abundances, and now we can compare different disease models. So this is just with a wild type model, but right now I'm currently using this method to calculate those ratios using an Alzheimer model. And I want to see how that Alzheimer can lead into those different variations of the composition of isomeric species. So that's also something that we were trying to do. And with that, I wanted to conclude just a summary of what we've
stopped.
What we've developed so far. I've developed a method that is very fast, and it's compatible with imaging experiments. So we can now uncover where those double bond locations, isomers, are located in tissue, and we can we're optimizing the reaction of the singlet oxygen, so that we can improve the signals of the products, and therefore it can be quantitative. And this method is very inexpensive. We just need a laser pointer, a photosensitizer, and it can be applied in any research lab. Actually, you don't need to modify your instrument. I think that's the beauty of this method. And finally, that just with MS, just by fragmenting those molecules, we can generate fragments that are informative of where the double bond location is, and therefore we can identify, uniquely identify every species. So the specificity of this method is very high. And with that, I want to thank you all for the opportunity to talk about my lab, about my research. I think that's pretty much it. I'm very happy to answer any questions.
Thank you, Daisy. Very nice presentation, by the way. There is a question from Brenda. And first, she thanks you for your talk. It was really interesting, she says. And she asked, what do you think should come next in order to be able to apply this technique everywhere?
Well, actually, it can be applied. As I mentioned, that was the goal. That it's pretty inexpensive. It's pretty cheap, so it can be applied anywhere right now. It's just that now what I'm trying to do is optimize it so that it can improve the coverage. So generally, I can analyze like 15 or 20 species at the same time. I'm trying to expand the capabilities. Maybe we can do 50 species at the same time, so we can have the entire lipid isomeric profile of any biological tissue that I'm looking into. So that's pretty much it. And yeah, so right now it can be applied anywhere. It's just I'm trying to make it better so that we can also have better results.
Thank you, Daisy. I have a question. And I wanted to know, what is the criteria to choose the laser color, the solvent that you're using, and the tissues that you can actually analyze? Is it just, can you choose anything from these three, or is there any criteria to choose?
Yeah,
between these?
so for the photosensitizer, you need to know what's the absorbance spectrum so that you can see where is the absorption bands. And so you can have to match it with the laser, right? So right now, Rose Bengal, it's around 460, 480, depends on the solvent that you're using. And the laser, it's around 452. So it will absorb that energy in that range. So it's not that I can apply any laser with any photosensitizer. So I need to match that first. Also that the power of the laser, even though this is a laser pointer, we're using pretty intense laser pointers. So that we can actually convert, so that this reaction can happen in the microsecond time scale, and therefore be compatible with any imaging technique. And regarding the tissue, yeah, I can analyze any tissue. I've done uterine, brain, liver. Yeah, I can do any tissue. Yeah.
Thank you so much, Daisy. It seems that those are the two questions that are right now. And I want to thank you again for your time and for your presentation. I also want to mention that Daisy is actually REPU mentor of this year in the chemistry branch of the REPU program. So we thank you all your work.
Yeah, thank you.
Great, thank you. Next, we have Alexandra Aponte. She is a student at National University of Engineering in physics, and she did her work of the REPU internship at the University of Copenhagen. And her title is Analysis of the Importance of the Spectral Shape of the UHE Neutrino Flux for Particle Physics. Whenever you're ready, Alexandra.
Yes. Okay. Okay, hi. Yeah, today I'm going to present my project that is called Analysis of the Importance of the Spectral Shape of Ultra-High Energy Neutrino Flux for Particle Physics. It was done in cooperation with the University of Copenhagen, and my advisor is Victor Branco, whom I thanks a lot for his support and advice. So first of all, the objectives, and if you don't understand at first, it's okay. I'm gonna talk about them continuous during my presentation. So first of all, as the title says, is to find the relevancy of the spectral shape flux for the cross-section studies. and also to make a step forward to a model-independent measurement of the cross-section. So let's start with the basics because this presentation is about neutrinos, so we should know a bit of them. So first of all, neutrinos are fundamental particles, which means that they are not made by smaller particles. They oscillate, which means that when they born and travel, they can change their characteristics. They're elusive. They hardly interact with matter, so they are really hard to catch. And they are diverse. They can come from different places on Earth, on space. They can be created or obtained naturally. So in this case, for us, it's important to know where do ultra-high energy neutrinos come from. Well, some sources, in this case, astronomical sources, are star-forming galaxies, gamma-ray bursts, and active galactic nuclei. In these sources, the particles are accelerated and neutrinos with really high energies are shooted towards the universe. These energies can vary from tera-electron volts to exelectron volts. And these energies have never been achieved here on Earth, even for most powerful accelerators. So neutrinos gives us the opportunity to study the standard model in energies that have never been studied before. And also an important thing is that because neutrinos hardly interact with anything in space too, they can come directly from their source. So they can be an useful tool to study these atomic bodies. How can we find neutrinos? Well, I told you neutrinos hardly interact with anything, so people have to be really creative. One of the solutions is ice cube. Ice cube, as you can see, in comparison with, for example, the Eiffel Tower, is a really huge detector. It's located on South Pole and is practically using Earth as part of their detector. Neutrinos interact with the ice inside of it and send signals to the optical modules inside of it. But actually, IceCube is going to get an upgrade that is called Gen 2. And my work is centered on study how future measurements of this future detector are going to be. And as you can see, Gen 2 is quite bigger than the actual IceCube that is actually big enough. So how do we study neutrinos? In this case, for you, it's important to know two characteristics. The first one is the cross-section. It's really important because it gives you a characterization of how particles, in this case, fundamental particles, interact and which their properties are. So for particle physics, it's really important to understand and have a prediction of how the cross-section is. But also we have the flux, which, as you can see here, there are many models for ultra-high energy neutrino fluxes, and they depend on astrophysical models. So if you want to study astronomical bodies, you have to be able to differentiate from which of these models are the results coming from. Because if this is the correct model, then you can say which of these theories is correct. But if this other is the correct, then you have another answer. But if at the end you're not able to differentiate these shapes, then that's not going to be very good for the people who is interested in that. So what do we want to know? First, if we can reconstruct the flux with the bend rates obtained on the detector, and if that's possible, as I told you, are we going to be able to differentiate them? And if the answer is yes, then it's going to be good for study the space with neutrinos. But if the answer is no, that is also going to be good for particle physics, because as I told you, it's a step forward for an independent cross-section study. So something important here that I think is curious is that there are some hints that the shape of the flux is not actually that relevant. These two parts of these two fluxes come from experimental data, but they are different at the end. But they should be both correct. So maybe that's a hint that the shape is not that important. So now the method. First, I took the flux propagated through air, taking into consideration how neutrinos interact with matter inside of it. And As you can see, the angle is a very important factor because depending on the angle, the distance that the neutrino travels through Earth varies. So when the angle is 180, then you travel through all the diameter on Earth, so you have more attenuation. This is the original flux, and these are the attenuations for different angles. But also there are other factors like the cross-section. If the cross-section is higher, then neutrinos interact more, so there is more attenuation, as you can see here. Higher, more attenuation. Then with the flux that you obtain at the detector, you can compute the bend rates. In this case, you can see here for different models, different results for the bend rate. There are models like the Bamblet one that have really high bend rates, while this other one called Heinze, it has really low bend rates for different directions. And the last thing is to build a function that can calculate event rates with different normalizations. Normalization is, you can see, just as a factor that you're going to multiply for your standard model flux and your standard model cross-section, and you vary those values. So for example, for a different normalization of the flux, you can see how it just gave a bit higher values. And with that, you can make a function of the likelihood, which can be understood just as how likely is for us to confuse two results. With this likelihood, I'm going to compare two models, and one of them, I'm going to vary it with different values of the normalization and see how the likelihood ends for each of different cases. And well, now my results for the likelihood. First, I compare two really close fluxes. As you can see, they are similar. They have high on the same range of energies. So the likelihood, as you can see, even though all this part is zero, there is a big part and dense area of a likelihood that is high. But what's happened if I choose a flux that is quite different to the other one? Well, then the likelihood, the area of high likelihood gets smaller, but as you can see, there's still areas where it's likely for us to confuse these results for these models that are not quite similar. And then I compare these two fluxes that are very different from one another. One of have high points on different energies. One of them is really low, and the event rates are really different. Remember, the Bamblet had really high event rates, while Heinze had really low ones. Well, now the results are that likelihood gets smaller. It's in a smaller area, but it's still there. So it shows us that even though these models are very different, it's likely for us for certain normalizations to confuse them. So now as the conclusions, I show you first, attenuation is observed and is used as a way to obtain the bend rates for different models. And as you can see that for very different models, there's always a significant likelihood, even though it's in smaller areas. And lastly, as you can see here, it seems that this sphere can extend to this part. So these results gives us a hint that maybe will be interesting to study more values of normalization and see how much it varies. Thanks.
Very nice presentation, Alexandra. Thank you for it. Okay, so I have a question,
Yes.
and it's about like the next step. Like you told me that the idea is to build the next generation of IceCube, which is I think called Gen 2.
Oh, yeah.
So could you tell me a little bit of like based on the result, what decisions are taken in the construction? Like, do the sensors change or the size of the equipment changes? How does it relate? It gets translated?
Oh, yeah. Well, in my results, one of the things is that for calculating the bend rate, it's necessary to have a volume
And well, that changed because the detector changed its size. But an important thing, a part of that, is that this detector is going to have higher angular precision. With that angular precision, you're going to be able to have less error at the time of rebuilding the event rate.
Okay. Thank you, Alexandra. Very nice work, by the way.
Thank you.
Okay, so it seems like we have no more questions, so we can move on to the next speaker right now.
Okay, thanks.
Thank you again. So our next speaker is Oscar Castro. He's a student at UTEC, and he did his REPU internship at Baylor College of Medicine. And the title of his talk is Evaluation of PonderNet for Out-of-Distribution Generalization in Computer Vision Tasks. Whenever you're ready, Oscar.
Okay. Thank you very much, Kevin. I'm gonna share my screen. So let me know if you can see my screen.
Yes.
Yes, perfect. Okay. Good afternoon, everyone. My name is Oscar Castro, and today I'm gonna talk about my project that I've been carrying out during my internship at Baylor College of Medicine, working together with my mentor, Jose Ortega. And the title of my project is Evaluation of PonderNet for Out-of-Distribution Generalization in Computer Vision Tasks. So machine learning algorithms get superhuman performance, and as we can see in the picture, the machine learning algorithm decrease the lower rate of error, even though deep neural networks pay on out-distribution generalization and entity failure. So here we have two different scenarios. The first one is under generalization failures, where the model can generalize, but it's not enough. So for example, here we can see a cat. If we apply a little filter and change the texture of the image, the model recognizes this as a different object, for example, like an elephant. And in the other scenario is overgeneralization failure, where the model identify the objects, can generalize, but it's too much. So here the model can recognize this random pattern as a guitar, for example. And this kind of generalization is related to the complexity of the task. So here we have the same picture. That is a frog, but the first one is a clean picture, and the following we apply different scale of noise. So that means that we know a severity, that we're going to call it severity. So if severity is equal 1, we can recognize this approach easily. But if the severity is equal 5, it's a more complex to us to recognize a fraud. So what is a possible solution for OOD failures? So we propose PonderNet. PonderNet is an algorithm that learns to adapt the amount of computation based on the complexity of the problem at hand. So why are you using PonderNet? Well, PonderNet has already been shown to help in OOD generalization in a bunch of different simple vector tasks where the complexity of the task change. So as we can see in the picture, if PonderNet if the task requires more steps, more amount of computation, the PonderNet is going to use it to get a better accuracy. Can PonderNet help in OOD computer vision tasks? So we propose to solve this PonderNet plus ResNet 18 a solution. So PonderNet, this method requires an architecture that can satisfy the following expression, where we have the step function that here we use as an input an image and a hiding state, and we get as output the scalar probability of halting the adaptive hiding state, and the prediction. So let's make an example. So here we have a picture of a cat. So in the step 0, for example, we apply ResNet 18 without the last layer to have the embedding, and then we apply the glue. That is basically the step function. So we have the hiding state, and we get the adaptive hiding state, and we get the prediction and the scalar probability of halting. Like in this case, 10% of accuracy and 7.2 the value of the probability of halting. So what happened in the next step? So the accuracy improved, and the probability of halting increased too. In the following step, we get a better accuracy, and we get the scalar probability of halting increase. For example, if we have a maximum number of steps equal 20, if we have a better accuracy and the scalar probability of halting is around 1, the process will stop and will not use all the number of steps. So here we can reduce the amount of computation. So one of the most important things with PonderNet is the loss function that is based on the reconstruction loss. That is basically the objective function that helps to expect the loss over ponder time, and use a predefined loss, and use the cumulative probability distribution of halting that is just a scalar probability of halting at the stem n. And then we add this loss to the regularization loss that helps to promote the exploration of ponder time. And here we use two hyperparameters, beta and lambda p. We only focus this project on beta. We focus on beta in this project. And we use lambda p to calculate the geometric price distribution, and then to calculate the KL divergence. So what are the metrics that we're going to use to evaluate the performance of PonderNet? So we use three different data sets, two data sets to the identical distributed tasks. We use Cypher 10 and Cypher 100. In the left side, we can see some example of classes of Cypher 10. And the OOD task that we use the training model with Cypher 100 to test with these 15 corrections that are basically noises, with the 5 levels of severity. So as a result, we get that PonderNet just more steps for more complex data set. If we analyze the graph, we see that Cypher 100, the average number of steps is 9.88, and the average number of steps is Cypher 10 is 7.44. And we use the same hyperparameter for the both models. And we can see that the Cypher 110 get a better accuracy in comparison with Cypher 100. So we can conclude that Cypher 100 is a more complex data set. As I mentioned before, we only focus on beta. So we vary, we use different values of beta to see what happened with the number of steps. So we get that with a lower beta, the exploration increase and result increase the average steps. So we use the same hyperparameters to train all these models. To the following result, we only use beta equal 1 and beta equal 0.1. So with beta equal 1, we can see that is basically a constant value. So in this result, we get the average accuracy we tested with all the corrections that are the noises that I showed before. We get that in the severity 5, we can see that the PonderNet gets a little better performance in comparison with ResNet 18 and with PonderNet using beta equal 1. So beta with using PonderNet with beta equal 0.1 gets a little better result. A summary, PonderNet uses more steps for more complex data sets. Regularization loss has to increase exploration. A lower beta increases exploration, as a result increase average steps. A small increase in performance was obtained in OOD generalization in computer vision tasks compared to simple vector tasks. In the next step, next step is test cipher 100C using the hyperparameter beta that increase more the exploration, or the number of steps increase. If we get good results, we're going to explore the performance by changing the hyperparameter lambda p. If we get better results, we're going to increase the complexity of the task by changing the data set to ImageNet. So that is my project. Thank you very much to everybody. Thank you very much to REPU and Jose, my mentor. I'm glad to answer all your questions.
Thank you, Oscar. Very nice presentation. I actually have 2 questions in mind. The first one is out of curiosity, how long does this experimentation take? Meaning, until like from the moment you start running the code until you get your result? Is it on the order of days or hours? How fast is the turnaround?
Well, basically, it takes 1 day, but I use only 100 epochs. So for get better results, maybe if we use 1,000 inputs, could take, I don't know, 3 days to training one model, for example.
And is that on your personal computer or on a server?
No, I use a server. I use the Baylor College server. I think the Active Lab server.
Okay, sounds good. The other question I have is actually at the beginning of your presentation, you were showing us figures where the prediction fails. I was wondering if after this implementation, you have figures actually of how it performs better.
Can you repeat the question?
Yes, so you were in this slide, you're showing us that deep neural networks fail on out of distribution generalization and intuitive failures. And now you're implementing PonderNet. Is the result more like the data that you showed to us that we see the accuracy as a number of epochs, or is it like, can I also see an image of what the results are like?
Oh,
when
yeah.
you train?
Basically, the results are this. So maybe I need to show this picture. This one, I think. Yes. Basically, we use this example of the image that I use in OLD task. So the severity level 1 is more easily to get better accuracy. With severity equal 5, we get lower accuracy. So we can see in this one, we get a lower accuracy in the more complex tasks. The accuracy is no higher than 30%, but it's a good result, I think, because PonderNet gets a little better performance. But we need to continue working on this to get a better results.
Okay, thank you, Oscar. Very nice work, by the way.
Thank you very much.
Great. Let's move on to the next person now. It is actually Luis Alberto de la Flor. He's an alumni from UTEC, and he did his REPU internship at University of British Columbia. The title of his talk is Evapotranspiration Seasonality in the Amazon Basin, a comparison between experimental and remote sensing data. Whenever you're ready, Luis. Luis, I don't hear you actually.
Hello?
Yes, now it works.
Great. Hello, everyone. Thank you, Gavin, for the introduction. As he mentioned, this study was about the evapotranspiration seasonality in the Amazon basin, and we compared the experimental data to remote sensing data. So to understand this better, we must explain 2 concepts. The first one is evapotranspiration, which is a quantity that helps us understand water flow in an ecosystem. As we can see here, the hydrological cycle, and evapotranspiration consists of the combination of both evaporation from water sources and transpiration. So it also considers canopy interception, which is the interception of water in vegetation. And this is very important because it helps us understand the ecosystem dynamics under climate change and a change in land use, as we will see. Another important concept is the covariance method, which is used to measure the evapotranspiration by measuring the flux of water. For example, we can see here this device, which is the eddy covariance tower. And by using the velocity, temperature, humidity, and concentration, it computes the amount of water that flows from the surface to the atmosphere of a certain component. For example, here we measured water, but it can also detect many other components, such as carbon dioxide, for example. So satellite data was compared to the eddy covariance towers, and we used 4 remote sensing products, which are all these 4 models that come from satellite detection. And we did the analysis on this location, which is called Querencia in Brazil. And we took 2 regions, a one with agricultural ground cover and another one with forest ground cover on a time period from 2015 to 2017. So the objectives of this study were to provide a better understanding of the seasonal patterns of transpiration and evapotranspiration in the Amazon basin, to identify the role of vegetation in surface atmosphere interactions, and finally to understand and identify how evapotranspiration changes in different ground covers. What we found was that if evapotranspiration in the forest ground cover was generally higher, as we can see in this table. Most of the values, the average values, were higher for the forest ground cover. And for these models, FLDAS and ERA5, we found incoherences because of the lower resolution of the satellite, which had a resolution of 11,000 meters, while the MODIS and PML had a much higher resolution of 500 degrees. But overall, we found that this difference is because when across the year, the ground cover and the vegetation changes for the agriculture because of the crops, we will have a very unstable flow of the water, as we can see here. So these graphs show how the evapotranspiration changes over the years for the wet and dry seasons for both ground covers. As we can see, the trends were kind of similar for most of the models and also for the experimental data from the eddy covariance tower. We saw that during the wet season, values tended to converge more than during the dry season, and the PML model changed the most from the agricultural to the forest, as we can see. And also that the experimental data showed a very low fluctuations, especially for the forest ground cover. As we can see, the values for evapotranspiration are much more stable across the year than what the model data tells us. So when analyzing the transpiration component on the whole evapotranspiration, we saw that it is the largest component for the forest ground cover. As we can see here, it is almost always above 75% of the total evapotranspiration, but not always for the agricultural ground cover. As we can see here, it even falls below the 50% threshold. And overall, we can see that the values are much lower. And this is because, as I mentioned, we have a dramatic change in canopy activity because the crops change in the agricultural land cover, whereas in the forest, we have a much more stable canopy abundance. So here it is natural that we find that the flow of water due to transpiration of the vegetation is much higher. So the conclusions were that satellite models showed important differences when compared to experimental data. In the literature, some explanations for this are that these models fail to capture the canopy dynamics of most of forests, and even inside the Amazon basin, we will find very different values in different locations. For example, if we do the analysis here in Querencia, it would be very, very different than other locations across the Amazon basin. The ground covers did affect the evapotranspiration seasonality and intensity, and forests generally presented a 37% higher evapotranspiration and a 31% higher transpiration over the evapotranspiration. So the following steps would be to add further models to the analysis, for example, the GLEAM model, and also to explore, as I mentioned, more locations across South America, like these ones that have eddy covariance data available, so that we can see how this evapotranspiration and water dynamics change geographically. So thank you very much for attending this presentation. I want to thank Brenda, who supported me a lot during this internship, and that's pretty much it. Thank you, everyone.
Thank you very much, Luis. Very nice presentation. I have a question, actually. So this is very interesting data. I noticed at the beginning, this is mostly data from Brazil area. Is that correct? Or does it cover some of other countries?
Yes, that's correct. This is because eddy covariance towers are available for these locations that I showed here. So even though the satellite models cover the whole world as a whole, we can only compare to experimental data in these certain areas.
Okay, nice. Because actually my question was like, how do you go to like translate this to Peru, right? Like, and now you told me it's about the towers.
Yeah.
What is required to put these towers in Peru area?
Well, I think there are a couple of eddy covariance towers in Peru, but the access to the information is not as easy as it was for these ones that are up to date and readily available for the public to use.
I see. Okay, so it's politics actually.
Maybe, yeah.
Yeah, thank you, Luis. Actually, there is a question from Mac. He asks, why it was important to measure the ET? Is it an indicator of the reality of the place?
Actually, evapotranspiration helps us measure, for example, climate change in some way, because when we have a more intense dry season, for example, we will have much lower water availability. So knowing the dynamics of evapotranspiration help us know how intense will a draft B, and actually how can we know the impact of climate change on different areas. So that's one aspect, for example, of why it matters.
Nice. Thank you, Luis, and for your presentation and very nice work as well. We'll move on to the next person now.
Thank you, Kevin.
All right, next is Maricielo Baella. She's from Universidad de Trujillo. And I want to highlight that she's one of the few mentees that is actually located not in Lima, which is very nice to have. She did her internship in University of Lille. That's how I'm going to pronounce French now, just as I would do it in Spanish. And her title is Proteomic Study of Mammary Gland Tumor Organoids. So, Maricielo.
Thank you, Kevin, for the presentation. We'll share my screen right now.
Great.
Can you see my screen?
Yes, it's good.
Okay. Thank you. Thank you so much, everyone. And good afternoon. I am Maricielo Aella, and today I'm going to present the primary results of the internship I've been doing thanks to the PRINCE Laboratory, the University of Lille, and the REPU program. And also thank you to my mentor, Lidia Yaxawang. So first of all, let's take a look into the main topic here. So as we may know, breast cancer is one of the main causes of death in women worldwide. As we may appreciate here in this map, this disease is the top cancer related to women in the whole countries and can be caused by many factors. For example, the presence of a familial history of another member of the family, some genetic mutations, some factors such as alcohol or tobacco, and also some environmental factors. So this is why the research in cancer, focus on cancer, is one of the main fields of study nowadays. And there is many approaches to study of the development of new therapies, such as, for example, the 2D cultures, but using cell lines. But commonly, this does not take into account the tumor environment. We can also use animal models such as mice, but they are usually being controlled because of the ethical problems. And also we can use human models, but besides ethical problems that can delay the use of them, and there is also the difficulty to access to samples. Then what can we do to avoid these problems? We can use the novel approach of 3D culture, which is taken more deeply and replicates more the similarity between tumor or the organoid and the build that is performed from them. And one kind of 3D culture is the organoids. In this case, we will refer to them as tumoroids, since the tumor is built from the tumor and not from an organ. And this kind of 3D culture can be used to This can be used to study drug efficacy, toxicity tests, perform investigation of disease mechanisms, and make discovery of novel diagnostic tools, and also build some living biobanks for personalized medicine. So the study of organoids came together with the proteomics approach, which are also a novel way to improve the research in cancer. So what is proteomics? Let's take a look into the genome of genomics, the study of the genes. But when we are using genomics, we are not taking into account the alternative splicing of the mRNA editing. Then we can use also transcriptomics, and then we are not taking into account the translational modifications that could lead in the expression in more than 1 million protein isoform that conform the protein, which are the actual focus of proteomics. So in this way, proteomics led us to study deeply the study of biomarker discovery in order to improve the early cancer diagnosis and then take a deeply look in the tumor biology. So because of this, the objective of my research was to perform a proteomic comparison between duct tumoroid versus tumor samples to validate duct tumoroids as an in vitro model to study breast cancer. And in order to lead to this objective, I followed this methodologic workflow. First of all, it has to be the tumoroid culture, then perform the proteomic analysis, and finally make the data interpretation. So first, the tumoroid culture protocol was to take tumor sample from ducts, take some fragments, and centrifugate the digestion solution, culture cells in a matrigel. And I have to highlight here that we had 8 individuals with breast cancer, and the dogs were not induced with cancer. The cancer was naturally developed in them. We had 3 tumor samples per patient and 3 tumor samples per patient. And then the next step is sitting in a matrigel, wait 20 days for the organoid formation to finally have the mature organoid. And then I performed the proteomic analysis. I used the bottom-up approach, which is characterized by taking a sample from the breast tumor, perform the protein extraction, make a protein digestion to study the peptides with mass spectrometry, then make a bioinformatic analysis in order to identify the proteins, and finally interpret the data, the results. And the first result I have here is the proteins that were shared in both tumor and tumoroid. As we can see here, there were 1,955 proteins shared between them, which means that both samples has 83.9% of similarity, which is a very good number. Also, they differed in at least more than 100 proteins. But first, we will focus in the common proteins. In this heat map, we can appreciate that there were some proteins that were overexpressed and downexpressed. But what does that mean? Let's remember that I'm comparing here just tumor versus organoid, and I don't have any kind of control. So when we say that the protein is overexpressed in tumor, that means that in the organoid will be downexpressed and vice versa. So I take a look more deeply in the overexpressed proteins in order to figure it out with which biological processes were altered. So I have to highlight here these both biological processes, immune response and cell growth and maintenance, because as we can see here, they have more overexpression of proteins in the tumor sample. But when we take a look into the protein metabolism related proteins, we appreciate the contrary, because the tumoroid has more overexpression of proteins. Why this could happen? Because when the culture of the tumoroid is made, the medium is improved in order to make sure about the living of the cancer cells. But there are some cells that can that are not related to cancer, such as related to the immune system, or maybe fibroblasts that could be related to the production of these proteins that could die in the process. So this difference could be related to the lack of the tumor cell heterogeneity. And then taking a look at the exclusively found proteins, we can appreciate some biological processes such as immune response, apoptosis, and regulation of cell cycle that were exclusive in one of them. I have to highlight here that for the proteins exclusively found for the tumor related to immune response and apoptosis were related to the caspase pathways and associated to lymphocytes. But interestingly, the proteins exclusively found in tumoroid that were related to the cell cycle regulation were also related to the positively regulation of the caspase pathways, and in the same way with the apoptosis. So finally, as future directions, have to perform the complete analysis with all 8 dog patients in order to build a protein interaction network to figure out which specific pathways and processes are related or has been altered in the process. Then continue the protein profile comparison between tumoroid and tumor samples, and of course validate the similarity between tumor and tumoroid. I would like to thank to the team and the intern at the University of Liège, to my mentor, Dr. Antonella Raffo, who has been very patient with me, and of course to the REPU program. And if you have any question, I will be happy to answer them. Thank you so much.
Thank you, Maricielo. It was a very nice presentation. I actually have a couple of questions. The first one is, why were dogs chosen for this type of study in comparison to the humans?
Oh, thank you so much for that question. I have actually a slide here. So as we can see, that develops the exactly same kind of tumors in comparison with humans. So there is no also breast cancer in dogs that is really similar to humans, and also brain or melanoma, leukemia, lymphoma, and many more diseases. So they share similar environmental, genomic, anatomical, and physiological features with humans. So that's why the use of dogs in the long term could allow us to compare its tumors with actual human tumors, and with a really high confidence.
Very interesting. I would have thought that maybe primates like monkeys and so on would be better candidates for these comparisons, but I guess, is that true, or maybe they're similar?
Yeah, they're similar, but also it is easier to get samples from dogs than the primates, because we will have to induce the cancer in primates, but in dogs it's naturally developed, so it's also more ethical.
Very interesting. Another question I had, actually I will hold back and I will ask Andres' question. Does it matter that dog breeds tend to be highly inbred? Are your samples from any specific breed?
From no, there were not specifically. That does not matters actually.
So like, okay, does that mean that when you do the study, you choose all different types of breeds for the dogs, or was the study focused on a very specific one?
It was randomly chosen, because we didn't choose like in a specific breed of dogs, just
okay.
Random.
Okay, so there's another question from Mac here. In slide 10, you explained that the differences found in the results were because of the cell heterogeneity. What about the stage of development of the tumors?
Oh, we did not take into account the stage of the tumor, so I would not exactly like to tell you if this could have an influence in this study. Just focus on the cells.
Okay, thank you, Maricielo. I actually have one final question. Maybe I got it wrong, but at some moment, did you mention that there were no control groups? Is that correct?
Yes, there were not control groups. I just compared the tumor and tumoroid.
Okay, that sounds, I mean, I never done biology research, but what is the impact of not having a control group? It seems like really relevant to have control groups, actually.
Well, and it seems that I'm not looking for a level of expression in the proteins. It really doesn't matter if we use a control or not, because we are just looking into the difference in tumor and tumoroid, and not with a healthy cell. So I want to figure out what are the difference between this copy, I would like to say, and that is the tumor with the tumoroid. And if I compared with a control, I will be looking for a difference in the expression with the tumoroid and the healthy cell. So it would be another field of study, not the comparison just between tumoroid or in tumor.
I see. Thank you, Maricela. Very nice work.
Thank you so much.
All right, let's move on to the next speaker. Next speaker is Jaime Loaiza. He's an alumni from UPC, and he did his internship work at KTH Royal Institute of Technology. His talk is titled "A Pipeline for Analysis of Muscle Excitation Under Dynamically Consistent Conditions." Whenever you're ready.
Right. Thank you very much. Good afternoon, everyone. So as Kevin stated, my research is titled "A Pipeline for Analysis of Muscle Excitation Under Dynamically Consistent."
Just there's a little box in the top corner.
Oh, all right. Yes, thank you. That can be over there. Okay.
Great.
All right. So as Kevin said, my name is Jaime Loaiza, and I will be presenting this to you today. So first of all, we need to understand why we need to understand the human body, or why understanding the human body is important. In order to understand the human body, we need to first understand what the process of understanding the human body is, which comes through the following steps: excitation, activation, force. Simple way of understanding this is excitation relates to what would be a neural impulse, or your brain commanding your body to move. Activation, which would be your muscles receiving this information and acting upon it, and force, which is the exerted force that would result in an object or entity that you're interacting with. Now, in order to understand the human body, it's not as simple as understanding how something works in just one condition. The human body is prepared for different situations, and it works under different loads, speeds, etc. And in this way, it is important to understand the human body under various conditions, which would, of course, take a lot of time because there are a lot of variables that need to be studied. So in this case, we will be studying what concerns the lower limbs, or both legs, and under a gait cycle or a walking cycle. Now, why is this important, or why studying these topics is something relevant? Mainly due to two things, which are physical disabilities and the physically impaired. Physical disabilities and physically impaired are things that impact people worldwide, ranging from naturally occurring diseases, or the disability or impaired movement of certain limbs, to externally caused accidents, such as the loss of a limb, or illnesses such as Parkinson's. In such way, the studying of the human body allows us to create solutions for these problems. And the main solutions that you will see regarding biomechanics are external solutions, such as exoskeletons, and even in some cases, replacements in the shape of prosthetics. Now, going back to my research topic, we need to first understand what a pipeline is. A pipeline is something very simple to understand. It's a sequence of steps that allow you to process information. And sometimes they are tailored for specific applications. Think of it as a function. It has inputs that goes into a system, a function, or even a subsystem, which can consist of a sub-pipeline, and that generates in turn outputs. This whole scheme could be considered a pipeline, and therefore this is what we will be studying throughout what I studied throughout my research. Now, it is important that in order to create a base pipeline, we start by defining all of our variables. In this case, motion. Through the study of the movement of the lower body, we used what are called motion files. As you can see on screen, on the left image, we can see what seems to be a skeleton moving. This simulation is run from what is called a prescribed motion. We're telling the muscle to follow a certain type of motion, and we are telling the muscle to do it in a specific way at a determined speed, and whilst exerting specific loads or forces. In such way, it's important to maintain the same motion throughout our baseline of the pipeline in order to determine whether the pipeline works properly or not. Now, what are the main uses of the desired pipeline? There are two main uses, which are to make the pipeline computationally efficient. Simulating the human body is computationally intensive and can take hours upon days for a simulation to fully run. And it also needs to produce reliable simulations or reliable data. Now, how are we going to go about doing this? We're choosing to use the right tool for the job. In this case, the tool we're going to use is called OpenSim MoCo. OpenSim is a software developed by Stanford University, and MoCo is an additional software developed again by Stanford University that is used for muscle optimization and control. This is a sort of a model that has a wider range of tools, which you can arrange in a certain way to perform your own pipelines. And it usually takes in a model. It takes in certain goals or certain things you expect to achieve. Sometimes optionally takes in data. In this case, we will be using data, whether it's from muscle activity, external forces, markers, image recognition, etc. And it all gets processed, and after performing, it obtains a solution, which basically gives you what you were looking for. In this case, we will be looking for muscle activation. The proposed pipeline is the following one. We obtain experimental data, which was obtained thanks to KTH Movability Lab. We feed this into a muscle redundancy solver, which is a a generic model that will basically help us feed the proper information to our model. This will then get transformed into muscle coordinates, which is basically the motion file that the little skeleton you saw walking is following. And this will be fed into two tools. First of all, it will be fed into MoCo tracking tool, which will, of course, give us muscle states, which are the solution. The MoCo tracking tool is interesting because it's going to take the muscle coordinates and it's going to try to be as close to these coordinates as possible. So it's going to try to make the skeleton move as close to the coordinates as it can possibly can. And the second tool we're going to be using is called MoCo Inverse. MoCo Inverse does something differently. What it does is it says, okay, we have to follow the coordinates, but we can do it at our rhythm. So it tries to minimize muscle activation, which means it tries to use the least amount of energy in each muscle in order to get as close as possible to the coordinates. In this way, MoCo Track cares more about being loyal to the coordinates, while MoCo Inverse cares more about minimizing muscle activation. And again, it will generate some muscle states. Now, how does this all, what results do we get from this? Like, how do we test the pipeline? The way we do it is by analyzing muscle activation for different muscles on the lower body. First of all, we started with upper leg muscles, in this case, vastus lateralis, which is a thigh muscle. As you can see on the right, we have the graph that was obtained after running MoCo Track and MoCo Inverse through, after running the experimental data through our pipeline. You can see on the x-axis, we have the gait cycle, which is an entire gait cycle, which means like one cycle of your legs walking forward. And activation, which goes from 0 to 1. In this case, it only shows up to 0.6. And as you can see, MoCo Track, which cares more about coordinates, peaks higher than MoCo Inverse, which cares about minimizing muscle activation. This makes sense, as a more loyal following of coordinates will exert a much higher activation on certain muscles, while MoCo Inverse, of course, shows a lower activation on the muscles, as that is its objective. From this, we can conclude that for upper leg muscles, both models are working and they are consistent, as we can see that MoCo Track generates higher peaks and follows coordinates better, while MoCo Inverse generates lower peaks. What about lower leg muscles? In the case of lower leg muscles, we obtain a similar result. As you can see, we are gonna be discussing soleus, which is a lower leg muscle. Once again, x-axis gait cycle and y-axis muscle activation. The peak, again, for MoCo Track is higher, as it uses the extra activation to follow the coordinates more precisely, while MoCo Inverse, throughout most of the cycle, as you can see the orange line, tries to stay as close to 0 as possible, or aside from this peak that matches for both plots. From these two plots, we can conclude that the pipeline is therefore consistent with what we were expecting, and therefore we can consider it reliable regarding the inverse and track parameters that we have fed into the system. So in order for us to reach further work, we first need to conclude what we've been working on. The biggest limitation, or one of the most important conclusions to draw from this research, is the fact that this is only applicable to a model called the Rajagopal model. In this case, the Rajagopal model can be seen on the left. It only includes both lower legs. In this way, it is important that in order for a pipeline to be reliable or more reliable, to test it with other experimental data using other models like Ley-Arnold or Hammer. Moreover, this model uses what is called a non-compliant tendon, which if you think of your tendons on your hands, on your legs, they're like springy-like mechanisms. They're like wires that stretch. In this case, we did not use a springy-like tendons. We used stiff tendons. In order for this model to be more reliable or be more accurate with real life, we need to use compliant tendons. The reason we did not do this is because using compliant tendons makes the simulation go into a whole nother level of computation and require absurd amount of time. So talking about days to weeks for a simulation to fully complete. And finally, we tested the model for only a specific speed of walking, or a specific walking speed, which was the preferred walking speed for the test subject. In this way, we need to test the dynamic consistency in other speeds in order to determine whether or not the pipeline is reliable at different speeds and in different motions. Finally, I would like to thank a bunch of people, actually, mainly Israel Peña and Adriana Laurent, which were part of my team. Israel, PhD candidate from KDH, he basically guided me through the entire research, and Adriana, which was my partner through the internship. I would also like to thank KDH Royal Institute of Technology, the Movability Lab, who were caring enough to give us the information needed to perform research. And finally, thank the REPU program for the opportunity that was given for us. Thank you very much. That would conclude my presentation.
Very nice presentation, Jaime, and very nice work as well. I have actually a couple of questions. And so the first one is, could you go back like one slide before this one?
Sure.
Yeah, here. So the model mainly focuses in lower limb movement. And I noticed in the figure that, you know, the upper body, either the back or the arms are not shown. But actually I'm curious about how much would the upper part of the body would impact the behavior of the lower part of the body.
That's actually something that is very relevant. It's a very relevant question to ask. And it's something that Israel, my mentor, is working on, actually. Different models, such as Ley-Arnold or Hammer, include some upper body elements, such as the arms or the torso, sometimes even the whole body. Now, I am not quite able to divulge the research that Israel has been doing, as it's still not published. However, we can assert that Rajagopal is the most accurate model when it comes to representing the gait cycle, which in turn allows us to conclude that the arms and the head, the shoulders don't really have much impact on the dynamics of the lower body.
Thank you. The next question I have is about not the details about the pipeline, but now that the pipeline has been developed, is the pipeline going to be used by like other researchers around the world or in the lab? Like, what is the after you have validated the pipeline, what are the steps next that you have this pipeline can take, actually?
Okay, so yeah, so actually MoCo is a community that it's an open source community. So there's like a very nice community of people online who share their pipelines, they share their discoveries. And the idea is to, once the pipeline has gone through all of these scrutiny, through using different models, different speeds, and maybe using the compliant tenant, we can share it throughout the open source, the MoCo community, and help other researchers who are looking to use pipelines like these in specific applications. I don't know, maybe prosthetics, maybe disability or surgery planning. There's like a million applications for these types of models.
All right, very nice work again, Jaime. Very nice presentation as well. Thank you.
Thank you.
All right, so next we have the last speaker of this sessions block. It's actually Leia Barrientos. She's a student from PUC, and she did her work at Yale University, and the title of her talk is Automated Measurement of Isovolumic Relaxation Time in Cardiovascular Magnetic Resonance. Whenever you're ready, Leah.
Hi, thank you, Kevin. Are you able to see my screen?
Yes.
Yeah, fine. Well. Yeah. Well, hello, everyone. Thank you so much for attending my presentation today. My name is Lidia Barrientos, and today I will talk about automated measurement of isovolumic relaxation time in cardiovascular magnetic resonance. My mentor is Ricardo Gonzalez, and I will start with a brief introduction about cardiac events and imaging techniques. The heart cycle is divided into systole and diastole. During systole, acts and pumps oxygenated blood out to the rest of the body. It causes that the LV volume decreases, as it can be seen in this graph. During this time also, the mitral valve remains closed. During diastole, the LV relaxes, and after IVRT, the MV opens. Once the MV is open, the left atrium fills the LV with blood following this direction. Also, during this time and after IVRT, the LV volume starts to increase. But what is this isovolumic relaxation time? Well, it is a period where the aortic valve closes, and after that, the mitral valve opens. During this time also, the LV pressure rapidly decreases and the LV volume is maintained. IVRT aids the evaluation of diastolic dysfunction. It plays a key role in a broad variety of cardiovascular diseases, such as heart failure and atrial fibrillation. IVRT is commonly measured in echocardiography, which is the gold standard for diastolic evaluation. The method used to assess IVRT is Doppler effect to monitor flow below the mitral valve. The limitations of this technique is that it has interobserver variability and depends on the acoustic window. But CMR may offer a more measurement of IVRT volume assessment and systolic evaluation is method to assess IVRT. A limitation is that one possible way to measure IVRT involves manual annotations without standardized derivation. Then the problem my project wants to address is the lack of an automated method to derive IVRT in CMR. And the objective is to develop a deep learning-based method to automatically derive IVRT with high reliability in CMR long-axis scenes. In order to do that, CMR long-axis scenes of two-chamber view and four-chamber view were obtained. A four-chamber view allows to see the four chambers of the heart, and a two-chamber view allows to see only two chambers. In this case, they are the left atrium and the left ventricle. Both scenes were obtained in the longitudinal direction of the heart. During this project, MBNet was used. MBNet is a dual-stage serial neural network. It has as and as an output, it has the microvolve displacement curve and the
Leia, can I recommend to turn off your video? We don't have good internet connection.
That can be, yeah. Are you missing my?
Yeah, you're breaking up a little bit. So to hear you better, could you turn off your video, please, so that we can listen you better?
Yeah, it's okay.
Thank you, Leia.
Yeah, can you listen to me better? Yeah.
Yes.
Well, after the MB set the microvolve initial plane, and it tracked how much far in millimeters the microvolve has moved. Finally, MBNet derives the microvolve displacement curve, which is this one. This curve was used to measure the IVRT. The reason is that the motion of the microvolve can indicate the period where the microvolve is static, which is the period of IVRT. IVRT can vary between two different patients. For example, here we can appreciate a large IVRT of a patient 8, and in the next image, we can appreciate a shorter IVRT from another patient. In order to avoid noise, a convolution-based smoothing filter was applied to the curve. First, we have original curve that has a smaller IVRT due to the pronounced peak caused by noise. And after that, we have a smoothed curve that has a larger IVRT that is more similar to the value of the manual annotated curve. Then in the project, IVRT was estimated using the 5% of the microvolve peak displacement value from the smoothed curve. This method was chosen after testing several approaches. This includes curve curvature, standardization, and different smoothing functions. The dataset used to evaluate the method was the manual annotation data of Yale University from the set of MBNet that was composed of 32 subjects. This dataset was diverse in gender, age, and contained several pathological groups. The reliability of the IVRT derivation method was assessed with intraclass correlation coefficient, also known as ICC. An ICC close to 1 indicates similarity between values from the same group. In the first image, it can be appreciated the identity line. It has an ICC of 0.79, which is a good one. An ICC close to 0 means that values from the same group are not similar. For example, in the second image, it can be observed that the population doesn't follow a trend in the identity line. That's the reason why it has an ICC of 0.18. The clinical application of the project was assessed by comparing IVRTs of control group and IVRTs of patients with heart failure with reduced ejection fraction. This last group is characterized for the enlarged ventricles that doesn't allow to have a proper blood flow. Then an empirical test with Walsh correction was performed between the two groups. An empirical test is a statistical procedure that compares the average or means of two independent or unrelated groups to determine if there is a significant difference between them. Walsh correction assumes that both distributions have different standard deviations. As a result, we obtain that the automated method yield a good clinical manual measures. That's the reason why we obtain an ICC of 0.73. Also, when we did the plant plot, we obtain. This means that our method doesn't overestimate or underestimate values. In the imperative test with Welsh correction, patients with HFrEF exhibited significantly larger IBRTs compared to control group. The difference between means obtained was 18.44 and a p-value that was lower than 0.05. This means that our method can differentiate significantly IBRTs of different groups. As a conclusion, I would like to say from the smoothed curve is developed in this research project of similar methods to assess diastolic dysfunction. I would like to thank the above institutions for their support during my internship, and a special thank you to my mentor, Ricardo Gonzalez, for his kind guidance and dedication to the project. And also, I would like to thank my supervisor, Dana Peters, for her advices and support. Thank you all for your attention in my presentation, and if there's any question or suggestion, I will be glad to listen to them.
Thank you, Leia. Very nice presentation. I have a question, and it's actually about the translation between your work into a clinical setting. Is the methodology that you worked on, for example, something that you can have in a hospital already, or is it still, or what steps would you need to take it to a hospital?
Yeah, of course. This will be like the most visible clinical application. What we need, like, for example, to do in order to take it to a hospital, it would be to assess more groups that have diseases. For example, here we assess heart failure with reduced ejection fraction. So we will need to evaluate this project with more diseases. Also, in order to translate this to a clinical approach, it will be needed to perform a test with a measurement of IBRT, but in vivo, it will be needed to measure the IBRT with sensors and compare it with this method, because this is a non-invasive method to measure IBRT. So in order to evaluate its accuracy, it will be needed to compare this non-invasive method with the invasive methods that are already in clinics or hospitals.
I see. Thank you for that. Just a follow-up question. If you were to do these calculations with the patient next to you, how long do they take? Is it super fast, or is it something that needs to be taken for hours?
Yeah. For example, when you perform a CMR scan, it takes seconds. I mean, it's not that.
I think, Leia?
Hard, but there are different types of. The most difficult thing, hold the breath, and that. Yeah, do you hear me?
Yeah, but you broke for several seconds. Could you begin again, please?
Yeah, of course. You mentioned to me that you wanted to know how was the measurement. So
Yeah.
what I was telling you is that, do you hear me? Do you hear me?
Right now, yes, but I lost you for a few seconds again.
Yeah, of course. I think I can finish my answer to your question. Well, in order to measure these IVRT, what is done is a patient is scanned with a CMR. And this takes some seconds, it's not that large, but the principal problem is that some of these CMR scanners need that the patient holds the breath. And that's a difficult, it's a difficult technique. That's why CMR scanners that has like a lower rate, for example, only 13 frames, which is the one I am using, are more easy to take. So this kind of methods that doesn't need a total high frame rate that needs also more time to scan is valuable.
All right. Thank you, Leia, for your presentation and very nice work as well.
Thank you, Kevin.
Okay, so Leia's presentation was the last of this block. Now we have a break that is going to last approximately 25 minutes, and let's recombine here again at 3:30 p.m. Peru time.
Hi, everyone. Welcome back to our third and final block of the REPU Seminar 2022. Today, we're going to have 5 more presentations. The first presenter is Ursula Navarro. She did her internship at the University of British Columbia, and I actually was her mentor. And then Ursula will present about evaluating the water fluxes of alternative soil management strategies towards a sustainable and resilient agriculture in the Cerrado region in Brazil. Ursula, whenever you're ready.
Okay. Hello, everyone. I'm gonna share my screen. So, okay. Okay, so hello, my name is Ursula Navarro, and in this research, I am evaluating the water fluxes of alternative soil management strategies towards a sustainable resilient agriculture in the Cerrado region in Brazil. First, let's talk about where is the Savanna Cerrado. This belongs to Brazil and is located in the middle of it, and is considered to be as the second biggest ecoregion in South America. When it comes to the climate characteristics, is that it's a place that is tropical, and also the temperature on average is 18 degrees. And also it has been linked to a lot of agricultural use, especially to soybean, maize, cotton, and coffee. And the production of all this agriculture, it has made the place to become one of the most productive regions in Brazil. And basically because these were considered to be acidic soils, but because the production of it came with also the addition of lime fertilizers and new varieties of crops. That's why this region, it's with a lot of production in this place. But what has this all production caused in the environment? Well, basically that has multiple impacts. And some of the effects are the lower porosity, also has increased the bulk density of the soil. And what we're going to study in this internship was the evapotranspiration, how this was affected by this extensive land use change. But when it comes to evapotranspiration, we have to say that is the amount of water that comes from soil and also the plant. And both waters, let's say that it's sum up into evapotranspiration. And why is it important to assess this? Basically, because when it comes to knowing which of these strategies are good or bad for the ecosystem, we have to take into account the water fluxes. Because if this, let's say that a vegetable field loses a lot of water, then with the time, that would mean that the place would get drier and drier, and this will cause that the whole place dies somehow. And for this, we are assessing with biochar. And biochar is a product of sugarcane filter cake, basically with a process called pyrolysis. That is combustion process with the temperatures that go from 300 to 1000 with the absence of oxygen. And sugarcane filter cake, in this case, was produced to have biochar. And it says that there have been a lot of positive impacts, such as soil organic carbon, increasing of these values, also nutrient content and water retention. But there's still uncertainty on how biochar can affect water balance. That's why the objective of this study is to estimate the effect of biochar and water balance in an agricultural field in the Cerrado region. And we're doing this by using the residual balance approach, which basically the name is because we have the subtraction of different variables. For example, we have latent heat flux, net radiation, ground heat flux, and sensible heat flux. When it comes to latent heat flux, which is the variable that we care the most right now, is the energy that water uses to evaporate, to condensate, to freeze, or to melt. Net radiation is the balance between incoming or
outgoing energy. The ground heat flux is the energy gained or lost during below ground warming or cooling, and sensible heat flux, that is the energy the water needs to change its temperature. How was this made? Basically, what we can see in this figure, we have the study plots, which you can see closer in this experimental setup plot. We have 6 plots in this place, and we also have sensors in each of them. In this study, what we did was basically to assess only in the sensor that was in control data. And in this plot, we had no biochar and also no sugarcane filter cake, or like that was not pyrolyzed. But we also compared this with the tower data that is basically far from where the study plots were. And now, net radiation was modeled using tower data and data from sensors in the control plot. What we did first is import data from Excel sheets. We had a lot of data that range from 2019, and then what we had to do is to calculate net radiation. But net radiation also had another equations, but we don't have to be scared about these whole equations because it's just to calculate them using Python, and of course being taken into account the different units that each variable have. And that was the first result with long way out. And we obtained a good correlation between model and observed net radiation. Now, net radiation has to be pretty close to the one that we have in the tower data and the sensor, because we're assessing the energy fluxes that happens in the whole place. So both information is quite important that are pretty close to each other, and this is the result that we had. Then what we did is to calculate greenhouse flux as soil heat flux. And as I said, this also has been assessed with different equations. This sensor was in 5 centimeters underground, and these were the results that we had. And in this case, you can see in the slide this plot that is comparing the ground heat flux that comes from the tower and the ground heat flux from the sensor. As you can see, the information of both of them are not too close to each other, but are still okay because it doesn't have to be quite similar as it had to be in the net radiation case. Last, we calculate the sensible heat flux. And again, we use a lot of equations to assess this variable, and we obtain these whole numbers. And lastly, as this is the last step of this equation, we obtain the ET, which is the latent heat. And that's what we wanted to obtain at the first place. And as you can see, these are the results that we had from the sensors and this one from the tower. As you can see, again, like the numbers are not quite to each other, or are not quite close to each other, but still we can say that the confidence that we have in this whole code that we obtain with all this to obtain this result were accurate. And well, my conclusions are that water flux from the control plot was modeled using the residual balance approach method quite successfully. It is recommended to measure the water fluxes from all the plots. Again, as I said, I only assessed the water flux from the control plot, but then what you have to do is to calculate in each of them plots to see how different is using the biochar at different concentrations. And lastly, the accuracy of latent heat flux depends on the amount of information obtained by the sensors. Though, of course, like the bigger amount of data you have, the better the results will be. And that's it. Thank you.
Thanks, Ursula. I will now like to open the floor for questions from the mentees. So any mentee that has a question can raise their hand and unmute themselves, or write your questions in the chat. Okay, if there are no questions from the mentees, anyone can ask their question. Actually, I do have a question, Ursula. Oh, there is a question from Andres here, actually. So is biochar only made from sugarcane? Could there be other sources of biochar, and do you think it would matter for ET?
Well, I think that first biochar can be made of different organic waste. It doesn't have only to be sugarcane. It could be any agricultural waste that you have in the place where you want to do your study, and it has been done so far very successfully. And if I think that it would matter for ET, I'm not quite sure for that answer. I haven't assessed if it would be different to use another source of waste, organic waste, to have different amounts of evapotranspiration, but that would be also pretty interesting to study.
All right, great. Thank you, Ursula. And I have one last question. So when you're comparing the ET from the tower and from the plot, why do you think that, like, it doesn't look like they're that similar, right? So do you think there could be some sort of adjustments or revisions that you could make to improve that?
Yeah, maybe to have into account the dates where we obtained the information. All in all, before these results that I had, the latent heat flux were super different to each other. One were like -1000, and in the tower we had like 64, I think. So they were pretty bad. And then what we did was basically to modify some equations based on other studies too, and to complement all those were pretty helpful to have more like close results from each other. But then we will definitely have to do some adjustments. Could be also deleting some information that has no like nothing to do, or like super far from each other, and maybe we can obtain something better.
Great. All right. Thank you, Ursula. Thank you. You did a great presentation. And for me, it was great seeing how you improved over time too, like from where you started to where you are right now. So good job.
Thank you.
Okay, now we're moving on to our next presentation. And it's Adriana Laurent. She is from the nanotechnology branch. Her mentor was Israel Peña, and she worked at Carteja Royal Institute of Technology. And she will tell us about her research titled Comparison between two simulations of the Rajagopal musculoskeletal model. So Adriana, whenever you're ready.
So you see my screen?
Yes.
Okay, perfect. So hello everyone, my name is Adriana Laurent, and I want to present my research project in the KTH Movability Lab. The name of the research is a comparison between two different simulations of a Rajagopal musculoskeletal model. So let's start with an important topic that allow understand all the project. So the gait cycle consists in one cycle of the stand phase and swim phase in one limb. So the stand phase occupies 60% over the gait cycles and start when the heels strike the ground and end with a push off to free the foot from the ground. And the swim phase occupies 40%, and it begins after toe off, and then when the heels strike the ground to start another cycle. But some diseases generate gait disorders. So for example, crouched gait. This is a gait disorder is common among patients with cerebral palsy. And it's easy to see the excessive ankle, knee, and the hip flexion during walking. Or neuropathy gait is generated by diabetics. Sorry, I think I have a delay here. you can see my screen?
Yeah, we can see your screen.
Okay, I don't know why. Okay, well, basically, the people who have diabetic disorders have a damage in the motor neurons. So they show muscle atrophy. So you can see in this video, probably the hip move just like upper, and then the movement of the foot is just like swim like that. And that is why it's important to know about the gait disorders. So, what are the benefits to use musculoskeletal simulation? Well, you can simulate different subjects with all the characteristics, weight, size, and etc. In simulation, you can create a assistant device, study different gait cycles, such as a crouch gait, or also modeling different animals like chimpanzee or ostrich. So one of the free simulators is OpenSim. You can generate simulation, analyze results, and create publication worldly graphic all in one. And this graphic show how biomechanics research think about OpenSim. So it's a start with neural comment that either generated by optimized controller or EMG. This drives the dynamic of the muscle forces generation. And this muscle forces generation create moment using the base, the musculoskeletal geometry. And the moment with multi-body dynamics, such as ground reaction forces, and also the body acceleration, all of them integrated, and then show me the motions. So OpenSim have different simulator methods. All of them have disadvantage, such as the time, sometimes it's hard to use, etc. Here appears OpenSim Moco, which has the best of every method. So Moco resolves 4 important problems: estimating muscle forces, finding model parameters, predicted motion, and optimize diverse parameters. So I asked about how does reference position derivative, which is an input, affect the simulation pipeline in OpenSim Moco. For methodology, I use all the data from Russia Global paper. So the data was collected using the camera, markers, and also a software. So all the data obtained was the models, the markers, and some track markers, like here. In the next step, I create a type of pipelines with MATLAB using the input, which is a track reference positions. So remember, this pipeline can permit simulate forces on torque generated for subjects. So I create 2 pipelines using one of them. It's the letter A. I use the pipeline with this input, the track reference position, and the second one, it's the second pipeline. It's the same pipeline without this input. So I run in OpenSim Moco, and OpenSim Moco give me the data solution and also the motion. So let's see the result. You will see what happened, for example, with the hip. You can see how the hip rotation changed over the gait cycles between simulation A, which is the blue line, and simulation B, which is the red line. But what happened with the forces? Reserve actuator is a force that needs the simulation to do more realistic. So you can see, for example, here in the knee, you can see the difference between two simulation, and this forces this for the simulation B, it's closest to 0 if you compare with the simulation A. The same thing happened with pelvis actuator. Pelvis actuator is a forces that need the pelvis to do more realistic the simulation. So you will see the difference between the simulation A and the simulation B, it's closer to 0. So what forces affect the muscle activation? So the soleus is one of the most important muscles. You can see the activation is different between simulation A and simulation B. Simulation B shows overactivation. That's because the forces in simulation B was less than the simulation A. That is why then the muscle needs the overactivation. Then what happened with the speed? So it's easy to see the oscillation in the first part of the gait cycle. That's because the track convert the data, the joint angle into the velocity. And obviously, if you don't put this input, this oscillation this input gives you this oscillation. So finally, the reference position derivative changes the simulation. So affect the muscle excitation and the fiber length. Also, the muscle velocity in simulation B is not physiological possible because you will see all the oscillation. It's not real. So simulation A is closer to physiological behavior for muscles in the human, and also is recommended to use if you like to run some pipelines. And also it's because they give you the improvement, the performance for your simulation. So thank you very much.
Thank you, Adriana. That was a great presentation. Okay, let's go with the questions. Who has a question for Adriana? Okay, Adriana, actually, I have a question. What do you think are the next steps for this type of research?
Yeah, basically now I did a comparison with 3 type of models. So basically every model have different value from the joint, from every joint. And I compare 3 models, just like Hammer, just like the Lane Arnold, and also Rasha Gopal. And at the moment, I know Rasha Gopal model have the best. I can say the best because it's closer to the reality. So basically, at the moment, I can say Rasha Gopal is the best model.
Great, thank you. And then I have one more question. Are there any techniques, like maybe wearing an instrument in like the human body or something, that you could use to like compare your models to like what is actually happening?
Yeah, basically all the data is you use some markers. So you use a software that you can see the movement of the subject. So you obtain all this data and you try to compare. But basically you use a markers for to find the data from every subject. It's interesting because change for different weight and also different size, and that is why it's a complex in simulation.
Great, thank you so much, Adriana. That was great. Okay, so our next speaker is Marcelo Hurtado. He's a mentee from the REPU biology branch. Her mentor was Mafe Senosain, and he did his internship at the Cancer Research Center of Toulouse. Today, he will be presenting on his work about a bioinformatic approach to identify genomic features that can predict patient response to immunotherapies in lung adenocarcinoma.
Thank you, Brenda.
Okay, so good afternoon to everyone. Today I will present my project with the Cancer Research Center of Toulouse, a bioinformatic approach to identify these genomic features that can predict patient response to immunotherapies in lung adenocarcinoma. So to start a little bit with the project, let's talk about immunotherapies. These are treatments that are used to face cancer, and they use the immune system from the patient to kill the cancer cells. A common immunotherapy is the PD-L1 that is based on the binding that happens between the tumor cell and the T cell. This binding is based on the PD-L1 from the tumor cell and the PD-1 from the T cell. This binding inhibits the T cell from killing the tumor cell. So current immunotherapies use an antibody called an anti-PD-L1 to block this binding and allow the T cell to kill the tumor cell. However, the problem is that not all patients respond well to these immunotherapies. So there could be some group of patients that will have a good prognosis and some others that will have a bad prognosis. No matter if their tumor is on stage 4, in stage 1, or maybe they have early stage tumors like a stage 2 or stage 1, they could also have a bad prognosis to these immunotherapies. So until now, medical centers do not know exactly which patient will respond or not to the treatment. And so far, there are no obvious factors that determine which patient will respond better. So as a consequence, we have more amounts of money are spent, and the immune system after a treatment of the patient get weak. So our purpose is to predict the response to these immunotherapies in order to bring us closer to improve personalized medicine. To have a group of patients with different clinical characteristics that could have different treatments and different immunotherapies, and at the end have a better prognosis for everyone. Our methodology is based on 3 data sets from lung adenocarcinoma. The first data set is from the Lung Predict project developed by the CRCT, the Cancer Research Center of Toulouse. The second database is from the Vanderbilt University, and the third cohort is from the ImmunoPredict project, another one developed by the CRCT. The 3 of them are RNA-seq data, and the first one have 61 samples between late and early stage tumors. The second database has 76 samples, mostly of early stage tumors, and the third cohort have 21 samples between late and early stage tumors. So in total, our data is composed by 158 samples. For our methodology, we have developed the pathway analysis based on our gene counts. These are the genes that we have used for our RNA-seq data. And with these genes, we have group and divide the genes from the pathway in which they are enriched. So different pathways have been identified in order to have finally a pathway score. This pathway score is based on the number of genes that this pathway include inside the metabolomic signal. Then we have developed the deconvolution analysis. This deconvolution analysis is based on the RNA profile from the immune cells. Then with this, we developed a signature matrix with the gene expression of each immune cell. This signature matrix helps us to, with our gene counts, develop a deconvolution method. In this case, the deconvolution method is called EPIDISH, in order to estimate the immune cell proportion of each tumor sample. We also have developed a transcription factor analysis to estimate the relative transcription factor activity on each sample. So we have, again, our gene counts per sample, and we developed and grouped the genes according to the transcription factors in which they are regulated. With this, we developed the algorithm, the Viper algorithm, to estimate the score for each transcription factor. This score is based, again, in the number of genes that they regulate in the samples that we are analyzing. At the end, we end up with the regulator activities of
this score, right? So before going into the results, let's see a general framework for the description of the results that we are going to see in the following slides. So this is an example of a heat map, and we have a C-score that will show a high expression in red and a low expression in blue. Then at the bottom, we are going to see some samples, the tumor samples, and at the right of the heat map, we are going to see the features. These features could be pathways, genes, transcription factors, or immune cells. Then at the top of the heat map, we are going to see some annotations. These annotations are based on the tumor and the patient's clinical characteristics. We have 3 clusters here that are divided by columns, and this cluster have been made using the K-means clustering, and we are using we are focusing on the stage and metastasis characteristics for analyzing our results. So now, the first result said that unsupervised analysis identified 2 groups of late-stage tumors with 3 different differential pathway activities: tumor development, tumor fatty acid metabolism, and cell cycle. So we can see here that this cluster has mostly late-stage tumors, and this other cluster have also late-stage tumors. Remember that late-stage tumors have a color have a darker color. So in the right side, we can see that they have a low expression in this group of pathways, but at the same time, the other late-stage samples on the left have a high expression in the same pathways. And this behavior can also be seen for the second group of pathways. The left side, we can see a low expression in the late-stage samples, and in the other late-stage samples, we can see a high expression in the pathways related to tumor acid metabolism. And the behavior repeats here from the cell cycle related pathways. From the transcription factor, we can see also that some late-stage samples have a higher expression in proteins related to cell cycle and a low expression in the ones of tumor development and immune response. Here, a high expression on the left side in tumor samples late stage, and a low expression in the other late stage group. For tumor development, for immune response, and for cell cycle. This behavior can also be seen with a differential gene expression analysis between late stage and early stage samples. In this volcano plot, we can see that at the right part, the upregulated genes, this means the genes that are high expressed in late stage samples, and in the left side, we can see the genes that are downregulated or have a low expression in late stage samples. For example, this gene, the KNSTRN, have been identified to have a high expression in patients with lung adenocarcinoma, be highly related to a poor overall survival in these kind of patients. In the other side, we can see that this gene, TP53ENP1, have been revealed to act as a tumor suppressor. So that's why, in this case, this gene is downregulated in late stage samples. The gene set enrichment analysis indicate that these genes that we have seen before are related to cell cycle and mitochondrial biogenesis. This means the ATP production. So at the end, our final remarks said that these late stage tumors mainly divide in 2 groups with differential expression activities related to tumor development, cell cycle, and immune response. And why is this important? Because now we can start making hypotheses about the behavior of the patient that will have these immunotherapies. For example, some patients that have a higher response in pathways related to immune system maybe will respond better to immunotherapies like the PD-L1 that is based on using the T cell production on the immune system. Well, these findings could help to identify which patients are more prone to respond or not to this kind of immunotherapies. So for our future direction of this project, we can corroborate current findings using other lung adenocarcinoma databases with information now about patient response to certain immunotherapies, and also apply machine learning methods to predict possible responses based on these gene expression results that we have seen. So finally, I would like to thanks to my main advisors, Mafe Senosain and Vera Pacanlin, also to my REPU advisors, Andres and Cayetana, and to the CRCT collaborators, and to the Mason Lab from Vanderbilt University. So that's it. Thank you so much. Thanks, Marcelo. That was a very, very good presentation. I really enjoyed the way you put up your introduction. That was very, I learned a lot from it. So good job. Okay, so let's see who has a question. You can unmute yourselves, or you can write your question in the chat and I can read it. Okay, we have a question from Andres. Is the idea to do RNA sequencing in patient tumor samples before treatment? Yes, well, the idea here with this project is to have our first insight of how will be the behavior related to gene expression in some patients, right? But at the end, the main goal is to develop, like, for example, a software that using these machine learning algorithms estimate or predict the response according to these genomic expression patterns. So yes, in fact, if we do that, we will need the RNA-seq from the tumor sample of each patient, right? Great, thank you, Marcelo. Okay, I think we can move on to our next speaker. So up next is Roy Peña, and he is from our nanotechnology REPU branch. His mentor was Rosa Diaz from Purdue University, and he will tell us about his research on intensity maps and segregation at interfaces of semiconductor quantum wells by aberration corrected stem. All yours, Roy.
Okay, thank you, Brenda. Hello, everyone. Can you hear me and can you see my screen?
Yes.
Okay, thank you. So as Brenda said, today I will present intensity maps and segregation at interfaces of 3-5 semiconductor quantum wells by aberration corrected stem. For the introduction, I want to start with the importance of this project, which lies in quantum computing. As you know, quantum computing is getting quite popular because it promises applications where it will be more efficient than conventional computing. It works with qubits instead of bits as the basic unit of quantum information, and we can generate topological qubits at the two-dimensional electron gas superconductor interface. A quantum well is a two-dimensional electron gas system. We will see more about this later. For now, I just want to show you that if we have a quantum well like this one, and if we have a superconductor cap layer above our system, we can generate topological qubits for quantum computing. But before that, we need to improve the performance of the quantum well in this topological qubit generation. So it turns out that the chemical segregation affects on this performance, and that's why we need to measure it, because if you can measure it, you can control it. Another important thing is STEM, which stands for Scanning Transmission Electron Microscopy, and it means that a microscope, but we don't use the light like normal microscopes. Instead, we use an electron beam, because electrons have a smaller wavelength and we can achieve an atomic resolution. So the electron beam is scattered by the specimen, and we have to collect these scattered electrons in this head-up detector so we can reconstruct the image. In the present study, we work with quantum well images like this one, and a quantum well is generated in this kind of heterostructure. As you can see, it's just a sandwich of really thin layers of semiconductors in a nanometric scale. In this case, we have gallium arsenide and gallium arsenide. But what is a quantum well? So if you focus on the conduction band and the valence band of our heterostructure, we can see different energy levels because we have different materials. Therefore, we will have an electron confinement and a hole confinement in this well. So that means that the electrons and the holes cannot escape because they don't have enough we will see the objectives of the project. We have three. The first one is characterize the quality of quantum wells. The second is obtain the intensity maps to show the chemical segregation and interface roughness of the quantum well. And the last is get metrics for the chemical segregation and interface roughness. So starting with methods, first we have to obtain the sublattices in the pterostructure. So here we have our quantum well image, and it has been normalized using ping-in-beam, as you can see here in this intensity bar. So the darker regions are of the gallium arsenide, and the brighter region is of the gallium indium arsenide. In this single quantum well, we have two types of sublattices, the group 3 and the group 5. Group 3 just means gallium and indium atom columns, and group 5 just means arsenic atom columns. So the intensity of this image depends on the chemical composition of our sample, but it also depends on the thickness of our sample, because each dot here doesn't represent a single atom. It represents a column of atoms, as you can see here in this figure. Knowing that, we can recognize all the atom columns finding the intensity peaks of this image, and we can replace them by red dots, as you can see here. Next, we have to construct the zone axis. Zone axis is this kind of arrangement of layers in a certain direction, in this case, the vertical direction. After that, we can classify the two sublattices, taking the odd and even layers. So the first sublattice represented by red dots are just the even layers, and the other lattice, which is represented by blue dots, are the odd layers. Once we have the atom positions of each sublattice, we can see how is the surface segregation in the intensity map to characterize it. But first, we need to know what is surface segregation. So surface segregation is an expected behavior during the growth of the quantum well, because if the growth were perfect, we would see this squared profile. But you know, anything is perfect, so in reality, it's more like this exponential behavior, and this is the Murakami model. The Murakami model is just these two equations. The first one is for the exponential rise, and the other is for the exponential decay. And the most important part here is this segregation coefficient, because it tells us how much segregation we have in our quantum well. So if S is equal to 0, the quantum well is perfect, like this square profile. But if S is equal to 1, we won't have a quantum well, because we will see a full segregation in the pterostructure. Great, now we can pass the results. As I said, with the two sublattices recognized, we can plot the intensity maps for the group 3 sublattice and for the group 5 sublattice. And again, we have the intensity normalized using ping-in-beam. So if you remember, in group 3, we have gallium and indium, and in group 5, we just have arsenic. So since we just have arsenic here, this plot represents the thickness variation of our sample. And here we can see the segregation of the quantum well at the middle, but we need to characterize this segregation. So in order to characterize quantitatively this segregation, we need an intensity map that only depends on the composition. And that's why we need the group 5 sublattice, because we need to do the thickness compensation, and then we need to normalize to the nominal composition, in this case of indium. Why indium? Because again, you have to remember that here we have gallium, here we have gallium and indium, and here we just have gallium. So the segregation will be of indium. Additionally, we can take the mean value of the vertical layers to obtain the composition profile. Here we can see the average indium composition in function of the position in nanometers, and we can see that we can see a similar behavior because it's just the mean. The last part of the project is fit this chemical segregation using the Murakami model. Here we have our previous plot, and we have to select our quantum well above a certain lower limit, and then we just perform the Murakami model fit. And if you remember, the most important part in the Murakami model is the segregation coefficient, which for this case is 0.7, and we also have an R-squared parameter. But what if we don't average all the layers and we perform the fitting for every layer? How would be the segregation behavior? So first of all, we will have a segregation coefficient for each layer. And we will have a plot like this. The segregation coefficient is a function of the number of the layers. And we can average all the dots to see the average segregation coefficient, which is 0.75. And you can actually see that it's a little bit higher than the previous one. Just to sum up and just to remind, S equal to 1 means that there is no quantum well. S equal to 0 means that we will have a perfect quantum well. And we have two segregation coefficients, one for the average composition fit and the other for the layer by layer fit. And as I said, the second one is a little bit higher. So finally, I can say the conclusions. First, the group 3 and the group 5 stuff lattices were classified based on the position of the atom columns, allowing us to obtain the intensity maps. Second, using the nominal composition and the thickness compensated intensity map of the quantum well, the composition map was obtained to characterize the roughness of the quantum well. And last, the Moroccan model was chosen for the fitting, showing a higher segregation coefficient for the layer by layer fit compared to the average composition fit. For the acknowledgements, I just want to say that I am very grateful to my mentor, Dr. Rosa Diaz, and to the whole REPU team. That's all. Thanks.
Thank you so much, Roy. That was a really good presentation. Okay, let's start with the questions. I actually have a couple of questions, but I want to open the floor first for mentees. So if any of the mentees have any question, please unmute yourselves or write your questions in the chat. Okay, seems like there are no questions, so I'm just going to start with my question, Roy. So in this case, you were segregating indium, right? But I was just wondering, out of curiosity, if you think this method would work for other metals or semi-metals, or if it's very specific to indium in this case.
Yeah, actually, it could work with other semiconductors because the title is 3-5 semiconductor quantum wells, and actually you can do this analysis to other semiconductors of 3-5 groups.
Great, thank you. And then we have a question from Jairo in the chat. Can this process be automated so that it can be applied to different samples? If so, what should be taken into account?
Yeah, actually, that process is a little bit tricky because you have to take into account a lot of variables. Every quantum well is different, so we can try, but we need to consider a lot of variables, as I said.
Great, thank you. And then I just have one last question. So, what can you do in terms of making this quantum wells so that you can have the number closer to 0, right? Because you want to have like the perfect quantum well. So in terms of like experimental or I guess lab data or the construction of these quantum wells, what can you do to make this number go lower?
Yeah, that question is related to the growth of the quantum well. I don't know so much about growth. The only thing I can say that is maybe some parameters like the temperature or the velocity of how you are growing your quantum well could be variables to have to improve. You know, the goal is to have a 0 S coefficient, and we need to consider some variables like the velocity or the temperature of the growth. As I said, I am not a grower, so I don't know so much about that, but that's what I can say.
Great, thank you so much, Roy. That was a very good presentation. Okay, so we have one more presentation today, and it's the turn of Brenda Tafur. She's a mentee from the computer science branch. She was mentored by Gisela Villarano from Baylor University, and she will present her work on the analysis of a set of experiments with neural networks model for Peruvian sign language interpretation dataset. So Brenda, whenever you're ready.
Thank you, Linda. So Okay, so hello everyone. Today I will talk about my presentation, which is called Analysis of a Set of Experiments with Gated Model for Peruvian Sign Language Interpretation Dataset. Okay, so my work is based on a paper by Dr. Bellarano, Perusil, which is submitted, and it contains the dataset Aprendo en Casa, or AEC. Aprendo en Casa was a Peruvian education show and the authors selected 2 subject videos from this TV show. And that contains unique signs and more than 2,000 instances. So here we have different signs, for example, comer, aprender, respuesta, and we have instances per sign. For example, aprender 1, 2, 3, 7. And at this time, we have different number of frames per instance. So we can have 10 frames for aprender 7 and 15 frames for aprender 10. And so on. So how can we track that science? Well, let me introduce MediaPipe. MediaPipe is a Google's open source framework that provides ready-to-use machine learning solutions to compute computer vision tasks. And we will use MediaPipe Post model and MediaPipe hand model. But let's focus in MediaPipe Post model. Well, as we can see here, MediaPipe predicts landmarks of the body. And we will use this model in our AEC dataset. So here we can see the sequence of frames for the idea sign. And these red dots are the landmarks. And notice that we are using only the landmarks above the waist. So what is our hypothesis? So as I mentioned before, MediaPipe provides different solutions, right? MediaPipe Pose, MediaPipe hand model, even MediaPipe face model. But let's focus right now in MediaPipe hand model. So our hypothesis is that adding finger landmarks to our post model will increase the accuracy of a k-nearest neighbors algorithms for sign classification. So we can see here that with MediaPipe post model, we have only 4 landmarks for the hand, for each hand. But what if we use MediaPipe hand model that provide us 21 landmarks for each hand? So let's find out. The methodology that we will follow is this. First, we will combine landmarks, pose, and so the pose and the hand model. Later, we will analyze the quality of the data, and the next step will be perform k-nearest neighbors and principal component analysis. So we have this set of experimentations, and we will use different parameters for these experimentations. For example, we will use 10 and 15 frames and instances, and in some experiments, we will have all the data set with all the signs, and another experiment, we will use the verbs only. Also, we have experiments with and without PCA, and we use the pose model only and the pose plus hand model. And the metrics that we use is the accuracy, and we split our data with 75% in the training and 25% in the testing. So we can see in this table the comparison of two sets of experiments. So we choose that set of experiments because we want to use the experiments that are most comparable. So here we have the same number of frames. We are using the same data set with VERS, the same number of components, the same classes, and even the same number of instances. And we can see here, like in the testing accuracy, we have like the better accuracy with k equal 2, and we have 54% with the only post model. And what about the post plus hand model? So we can see that the hand model is affecting in a negative way because we are not obtaining a better testing accuracy. So from this table, we can see that using PCA with 6 components, there is no increase in accuracy adding finger landmarks. And using PCA with 10 components, we have a similar scenario because we have a slightly better testing accuracy with only post model and with post plus hand model. But in general, we can see that the post plus hand model are not increasing the accuracy adding these finger landmarks. So from this table, we can see that using the 10 components PCA, there is not increasing accuracy adding finger landmarks. So this led us to the conclusions. So in a preliminary way, we can reject the hypothesis that finger landmarks increase testing accuracy. And this might have been due to the poor quality of the data, since 26% of frames do not recognize finger landmarks. But we're still not sure about that this is the main reason. We will only know once we clean the data and perform experiments again. And the best result we obtained was using the post-only model, in which we obtained 54% of testing accuracy with PCA 6 components and 62% with 10 components. And also, using 10 component PCA, the testing accuracy with model post plus hand increases on average by 10% with respect to PCA with 6 components. So thank you so much for your attention, and I will be glad to answer your questions.
Thank you, Brenda. That was very, very interesting. And yeah, I think these type of research projects are very, very important, right? Because we want to increase like accessibility. And I think that could be, these type of studies could be, could lean towards that. So I actually have a question that I'm gonna say right now, but if anyone else has a question, you can write it in the chat or raise your hand or unmute yourselves. But I was just like wondering about when you mentioned about the poor quality of the data and that the frames were not recognized, or that the frames do not recognize the finger landmarks. I was just wondering, why do you think that is? Like, what does it mean it's bad quality or poor quality? Is it like too far away? Maybe the hand movements are too fast, or why do you think that happens?
Yeah, so we realized that amount of frames doesn't recognize finger landmarks. So when we run the MediaPipe hand model, like I'm not sure about the reason behind that, why MediaPipe hand model is not recognizing all the landmarks for the fingers, but maybe I suppose that it could be because of the the quality of the image, you know, that they are not so clear. Where are the landmarks? Maybe if we have some fingers like closer, we can see that the tracking of the fingers.
Yeah, thank you. So do you think if you had only, like, let's say a video of like hands making like all the gestures, do you think that could be used to improve the model? So because it like the video or like the figure would only be the finger or like the full hand with the fingers, right? So do you think that could be something that could be used to improve the model?
Yeah, and also keep in mind that we are using MediaPipe pose plus hand. So maybe that could be like some kind of overlapping, because there are some signs that are closer to the face, and yeah, so some kind of overlapping even in the hands.
Great. Yeah, thank you so much for your answers. So yeah, that's it. That was our last presenter for today. So before we finish this stream, I would really like to thank all the mentees that presented today, but also congratulate them and acknowledge that this year has been very difficult for everyone. And all the work they have done is really impressive. We know COVID-19 isn't over yet, and there were many challenges, I'm sure, for all the projects because it's a virtual internship. But yeah, we are really impressed with all the work everyone has done. And yeah, I think it was very amazing to see your progress from day one to today that you're presenting your final project. So congratulations to everyone. And yeah, that concludes our REPU Seminar 2022 today. Thank you.